You are listening to Designing Data Systems, Principles for Scalable, Reliable, and Maintainable Applications. Subscribe to keep up to date on our latest audiobooks. Designing Data Systems, Principles for Scalable, Reliable, and Maintainable Applications. Chapter 1, Welcome to the Data Jungle. What are data-intensive applications? Imagine a world without data. No social media feeds updating in real time. No streaming services suggesting your next binge watch. No online maps guiding you through traffic. No e-commerce sites remembering your past purchases. It's almost unthinkable, isn't it? Data has become the lifeblood of nearly every application we interact with daily. From the moment you wake up and check your phone for the latest news headline, to the algorithms personalizing your shopping experience, data is constantly being created, moved, processed, and stored. For a long time, software development largely focused on the logic of an application. What features it offered, how its user interface looked, and how quickly it could perform computations. The database was often just a component in the background, something you connected to, stored a few records in, and didn't think much about beyond the occasional query. But this has changed dramatically. Today, the success or failure of an application often hinges not on its raw processing speed, but on its ability to handle, manage, and make sense of vast amounts of data. Data that is constantly flowing, evolving, and interacting in complex ways. When we talk about applications where data is the central challenge, where performance bottlenecks are more about sophisticated data processing than simple CPU cycles, we're talking about data-intensive applications. This shift means that designing software isn't just about writing clever code. It's about designing the data systems that underpin that code. It's about ensuring your data is always available, reliable, and can grow with your users. It's about understanding the subtle, yet profound, differences between various ways of storing and processing information. And that's precisely what this book aims to help you do. 1.2 Defining Data-Intensive. Beyond just big data. When you hear data-intensive, you might immediately think of big data. Those massive datasets, often measured in petabytes or even exabytes, that require specialized tools for analysis. While big data certainly falls under the umbrella of data-intensive systems, the concept is broader. Being data-intensive isn't merely about the sheer volume of data you have. Imagine an application like a messaging service. Does it have big data? Perhaps over time, but the real challenge might not be the total amount of messages stored. Instead, it might be velocity, the speed at which new messages arrive and need to be delivered. Imagine millions of messages per second during a peak event. The system must process this influx quickly. A delay of even a few seconds can be catastrophic for user experience. Variety, the different forms data takes. Messages might include text, images, videos, voice notes, emojis, and live location updates. Each type has different storage, processing, and display requirements. Validity, veracity, ensuring the data is correct and trustworthy. A faulty sensor sending incorrect readings or a system bug introducing bad data can have serious consequences. Value, how can we extract meaningful insights from this data? Can we use message content to identify trends, improve search, or detect spam? This often requires sophisticated analysis of all the data, not just samples. So, while volume is undoubtedly a factor, a data-intensive application grapples equally with velocity, the speed of data, and variety, the different types and structures of data. It's an application whose primary challenges revolve around these data characteristics, rather than purely computational complexity. Think of searching a vast library. The challenge isn't the speed of your eyes, but the organization and indexing of millions of books. That's a data-intensive problem. 1.3 The Big Three Pillars of System Design. When we talk about designing robust data systems, three fundamental concerns always rise to the top. Reliability. Imagine trying to hail a taxi from an app, and it crashes every third time you open it. Or you're trying to purchase an item online, and the website gives you an error message during checkout. These experiences are frustrating because the system isn't reliable. A reliable system is one that continues to perform its intended functions correctly, even in the face of adversity. What kind of adversity? We're talking about faults. A fault is a deviation from the expected behavior of a component. This could be a hard drive failing, a network cable getting unplugged, a power outage, a software bug causing a process to crash, or even a human operator entering incorrect configuration. Fault versus failure. A fault is not a failure. A failure occurs when the system as a whole stops performing its required function. The goal of reliability is to anticipate and contain faults so they don't escalate into full system failures. Think of a car with a spare tire. A flat tire fault doesn't lead to being stranded failure because of the spare tire reliability mechanism. Why it matters: users expect systems to work. Businesses rely on systems for their operations. Unreliability erodes trust and can lead to significant financial and reputational damage. Scalability. Let's say your taxi app is incredibly reliable, never crashes, and always finds you a cab. But one day, its popularity explodes. Now, instead of 100 users, you have 1 million. Suddenly, the app becomes glacially slow. Finding a taxi takes minutes, sometimes hours. This system is not scalable. A scalable system is one that has strategies for coping with increased load. What's load? Load can be measured in various ways. The number of concurrent users, the rate of requests per second, the total volume of data stored, or the hit rate on a particular API endpoint. How do systems scale? Primarily in 2 ways. Scaling up: vertical scaling, buying a more powerful machine, more CPU, more memory, faster disks. This is often simpler but hits practical and economic limits quickly. Imagine upgrading a single engine to a bigger one. Scaling out: horizontal scaling, distributing the load across multiple, smaller machines. This is more complex to design, but offers potentially unlimited capacity. Imagine adding more checkout lanes at a busy supermarket instead of just making one lane superfast. Why it matters: growth is a good problem, but unaddressed, it can turn into a nightmare. A system that doesn't scale well can't handle success, leading to lost users and revenue. Maintainability. Building a system is just the beginning. Over its lifetime, software will need to be changed, adapted, and debugged. Someone new will join the team and need to understand how it works. New features will be added. Bugs will be fixed. A maintainable system is one that is easy to operate, easy to understand, and easy to modify. For operators, can you monitor the system's health, diagnose problems efficiently, and deploy updates without causing downtime? Is it easy to add new monitoring or logging? For new engineers, can a new team member quickly grasp the system's purpose, design, constraints, and how its various parts fit together? Is the code clear, well-documented, and modular? For future developers, when requirements change, can new features be added without introducing a cascade of new bugs or breaking existing functionality? Is the system adaptable to new needs? Why it matters. Software is a living entity. The initial development cost is often dwarfed by the long-term maintenance cost. A maintainable system reduces ongoing expenses, improves developer productivity, and allows the business to adapt more quickly to market demands. This includes reducing the bus factor. How many people need to be hit by a bus before the project grinds to a halt? These 3 pillars, reliability, scalability, and maintainability, are often in tension. Improving one might make another more challenging. For example, adding more machines for scalability often introduces more potential points of failure, making reliability harder to achieve. Or, introducing extreme optimization for performance might make the code impenetrable, harming maintainability. Designing data systems is largely about understanding these trade-offs and making informed decisions based on the specific needs of your application. 1.4. A glimpse into the challenges ahead. As we delve deeper into the fascinating world of data systems, we'll strip away the comforting illusion of a single, simple database. In reality, most data-intensive applications don't store all their data in one giant, centralized database. They spread it across multiple systems: a traditional relational database for critical business data, a specialized search index for quick lookups, a distributed queue for live events, a fast key-value store for user sessions, and a data warehouse for analytics. Managing this sprawling landscape of interconnected data stores is a significant challenge, often called polyglot persistence. We'll also confront the inherent unreliability of networks. Whenever two machines need to communicate, there's a risk of delay, data loss, or complete disconnection. Messages can get lost, duplicated, or arrive out of order. This seemingly minor detail has profound implications for how we design systems that need to agree on a specific piece of data, or orchestrate complex workflows across multiple geographically dispersed servers. How do systems reach consensus in the face of such chaos? And then there's the concept of consistency, how to ensure that everyone sees the latest, correct version of data, especially when it's being updated simultaneously by many different users. Imagine two people trying to book the last seat on an airplane at the exact same moment. How does the system ensure only one of them gets it? And what happens if the system needs to deal with millions of such requests every second across distributed servers around the world? This isn't just a technical puzzle, it's fundamental to data integrity and user trust. 1.5 The journey starts here. This book is not a manual for a specific database product. It won't give you ready-made recipes for building the next social media giant. Instead, it aims to equip you with the fundamental principles, the mental models, and the critical thinking skills necessary to understand why various data systems are designed the way they are, what problems they solve, and where their limitations lie. By understanding these core concepts, you'll be better prepared to evaluate new technologies, troubleshoot complex issues, and, most importantly, design robust, resilient, and adaptable data-intensive applications that can thrive in our increasingly data-driven world. We will explore how data is modeled, stored, and retrieved, how it's replicated and partitioned for scale, how its integrity is maintained through transactions, and how it flows through modern batch and stream processing systems. Let's begin our journey into the data jungle. Chapter 2: The Unshakable Foundation: Reliability, Scalability, and Maintainability. In our first chapter, we introduced the concept of data-intensive applications and briefly touched upon the big three foundational pillars of system design: reliability, scalability, and maintainability. These are not merely desirable qualities. They are non-negotiable requirements for any system that aims to serve users consistently and grow sustainably. Think of them as the bedrock upon which any robust application must be built. Without a solid foundation, even the most innovative features will eventually crumble under the weight of traffic, technical debt, or unexpected failures. Let's delve deeper into each of these pillars, understanding what they truly mean, why they are so critical, and the approaches engineers take to achieve them. 2.1 Reliability: Building for resilience in a flawed world. Reliability means your system can perform its intended functions correctly and consistently, even when things go wrong. It's about building a system that anticipates problems and gracefully handles them, rather than collapsing. No component is perfect. Hardware fails, software has bugs, and people make mistakes. A truly reliable system acknowledges these truths and builds defenses against them. Consider the different sources of problems, often called faults. Hardware faults: these are physical problems. A power supply might fail, a hard disk could crash, a network cable might be unplugged, or a server rack could overheat. While hardware components can be repaired or replaced, the trick is to prevent these individual component failures from bringing down the entire application. Software faults: bugs are an inescapable part of software development. These could be subtle errors that only manifest under rare conditions, resource leaks that gradually degrade performance, or major logical flaws that lead to incorrect results or crashes. Predicting and preventing all software bugs is impossible, so a reliable system must also be designed to tolerate their presence. Human faults: people operate and configure systems, and people make mistakes. A misconfigured firewall rule, an incorrect database query applied to production data, or simply forgetting a crucial step in a deployment process can lead to outages. Designing systems that minimize opportunities for human error and providing quick recovery mechanisms is vital. This includes well-defined operational procedures, clear APIs that reduce ambiguity, and robust testing before deployments. The goal is not to avoid faults, but to tolerate them. Just as a modern car has multiple braking systems, airbags, and reinforced frames, A reliable data system employs various strategies to ensure that no single fault can lead to a complete system failure. Redundancy. This is a fundamental technique. Instead of having one server, you have two or more, so if one fails, others can take over. For hard disks, this is often achieved with RAID, redundant array of independent disks, where data is spread across multiple disks in such a way that if one fails, the data can be reconstructed from the others. For entire servers, you might have failover systems, where a backup server quietly takes over if the primary one goes offline. Cloud computing environments often abstract this, handling server and network redundancy for you, but the principle remains. Error detection and correction. Mechanisms like checksums can detect if data has been corrupted during transmission or storage. Some systems can even correct small errors automatically. Process isolation. If one part of a complex application crashes, it shouldn't take down the entire system. Designing components to be isolated from each other can limit the impact of a fault. Robust error handling. Code should not just crash when an unexpected input arrives or an external service fails. It should be designed to catch errors, log them, and respond gracefully, perhaps by retrying the operation, serving cached data, or informing the user of a temporary issue. Thorough testing. Unit tests, integration tests, end-to-end tests, and performance tests are all crucial in identifying bugs and potential failure points before a system goes live. Ultimately, reliability is about trust. Users trust that your application will work when they need it, and businesses trust that their vital operations will continue uninterrupted. Building a reliable system means thinking pessimistically, anticipating what can go wrong, and actively designing defenses. 2.2 Scalability. Growing with grace. Scalability refers to a system's ability to cope with increased load. What constitutes load depends entirely on the application. For a social media site, load might be measured by the number of concurrent active users or the rate of new posts per second. For an e-commerce site, it could be the number of simultaneous transactions or items added to carts. For a data warehouse, it might be the volume of data ingested daily or the complexity of analytical queries. When the load increases, how does your system behave? Does its performance degrade linearly? Does it simply stop responding? A scalable system is one that can handle growth without radically undermining performance or requiring a complete architectural overhaul. When discussing scalability, we often talk about two key performance metrics. Latency. This is the duration between a request being made and a response being received. For example, how long does it take for a web page to load after you click a link? Lower latency is generally better. Throughput. This refers to the number of operations that can be processed per unit of time. For example, how many requests can a server handle per second? Higher throughput is generally better. To handle increasing load, systems typically employ one of two primary scaling strategies. Scaling up vertical scaling. This involves moving to a more powerful machine with faster CPUs, more memory, or larger, quicker disks. Think of it like upgrading to a bigger, faster engine in a single car. This approach is often simpler to implement initially, as it doesn't require changes to how your application distributes work. However, there are practical and economic limits to how big a single machine can get. There's only so much you can pack into one box, and the cost can become prohibitive. Also, a single large machine is still a single point of failure, which impacts reliability. Scaling out horizontal scaling. This involves distributing the load across multiple, smaller machines that work together. Instead of one superfast car, you have a fleet of standard cars, each handling a piece of the journey. This is generally the preferred approach for true scalability in data-intensive applications. If one machine becomes overloaded or fails, you can simply add another. However, horizontal scaling introduces significant architectural complexity. Now, your application must deal with distributed computing. Network communication between machines, coordinating tasks, ensuring data consistency across multiple nodes, and handling partial failures where some machines are working and others are not. This is where much of the challenge and innovation in data systems lies. Consider a social media platform. As it grows, the number of users and posts explodes. Scaling up by buying a monstrous server quickly becomes insufficient. Instead, they scale out. User profiles might be stored on one set of servers, messages on another. New posts are spread across many machines to handle the right load. The feed, you see, is assembled from data that might live on dozens or hundreds of different machines. Each of these decisions about how to distribute data and computation directly impacts the system's ability to scale. Understanding the different ways to divide and conquer data is a central theme of this book. 2.3 Maintainability, designing for the long haul. Maintainability might not sound as exciting as reliability or scalability, but it is arguably the most crucial for the long-term success of any software project. A system that is difficult to maintain will eventually become a liability, leading to slower development, more bugs, and increased operational costs. Maintainability means designing your system to be easy to operate, easy to understand, and easy to modify and adapt over time. We can break maintainability into several key aspects. Operability. How easy is it for operations teams, DevOps, SREs, to monitor the system's health, diagnose problems, and deploy updates? Good operability means clear monitoring dashboards that show the system's vital signs, comprehensive logging that helps trace requests and identify errors, well-defined procedures for deployment, backups, and disaster recovery, easy ways to roll back changes if something goes wrong, automated tools for provisioning and managing infrastructure. Simplicity, reducing complexity. Complex systems are harder to understand, debug, and modify. Simplicity doesn't mean fewer features, but rather a design that is easy to grasp. This means clear, modular separation of concerns. Each part of the system has a well-defined responsibility, avoiding overly clever or obscure code, minimizing dependencies between components. Good documentation, though a simple design often requires less. Evolvability, adaptability, and modifiability. Software requirements change constantly. New features are added, old ones are deprecated, and business rules evolve. An evolvable system can easily accommodate these changes without requiring a complete rewrite or introducing a cascade of new bugs. This involves designing flexible APIs and interfaces between components, adhering to design principles that allow for pluggable components, having automated test suites that confirm existing functionality isn't broken when changes are made, regression testing, minimizing technical debt, which is the metaphorical interest paid on shortcuts or poor design decisions made in the past. Think of building a house. Initial construction is just one part. You also need to consider how easy it will be to live in, operability, understand its layout, simplicity, and remodel or expand it in the future, evolvability. A house that's hard to navigate, full of hidden dangers, and impossible to adapt will quickly become a burden, no matter how beautiful it looked on day one. 2.4 The interplay and trade-offs. It is rare to find a system that perfectly maximizes reliability, scalability, and maintainability all at once. Often, there are inherent trade-offs between these goals, and the art of system design lies in understanding these tensions and making informed decisions based on the specific needs and priorities of your application. For instance, reliability versus scalability. Adding more machines for horizontal scalability inherently increases the number of things that can go wrong, potentially making reliability harder to guarantee. More machines mean more network connections, more potential for network partitions, and more distributed state that needs to be coordinated. Maintainability versus performance scalability. Highly optimized code might be incredibly fast, but if it relies on complex, esoteric algorithms or hardware-specific tricks, it might be nearly impossible for new team members to understand or modify. A system designed for extreme scalability might involve highly specialized distributed data structures that are much harder to debug and operate than a simple, centralized database. Reliability scalability versus cost. Achieving very high levels of reliability, e.g., 5 nines of availability, meaning 99.999% uptime, or extreme scalability often requires significant investment in redundant hardware, specialized software, and highly skilled engineering teams. These resources might be overkill for a small internal tool, but essential for a global financial trading platform. The right balance depends on your context. A bank's core transaction system will prioritize reliability and consistency above almost all else, even if it means sacrificing some real-time responsiveness or requiring highly specialized hardware. A social media feed, on the other hand, might tolerate occasional data inconsistencies if it means delivering content instantly to millions of users worldwide. Prioritizing scalability and low latency. Every design decision, from choosing a database to structuring your application's components, will have implications for these three pillars. Throughout this book, as we explore different data system concepts, we will consistently highlight how specific choices impact reliability, scalability, and maintainability, allowing you to critically evaluate solutions and make better design decisions for your own projects. These three qualities, reliability, scalability, and maintainability, form the unshakable foundation for any successful data-intensive application. They are not merely abstract concepts, but practical concerns that shape every engineering decision. Armed with a deep understanding of these pillars, you are now ready to explore the exciting world of data models, storage, and processing, starting with how we structure and query the very data we aim to manage. Chapter 3. Modeling the World, Data Models and Query Languages. In our journey to understand data-intensive applications, we've talked about the big three: reliability, scalability, and maintainability as the foundational pillars. Now, let's turn our attention to the very heart of how we represent information: data models. A data model is essentially a structured way of organizing data and the rules for interacting with it. Think of it as the blueprint for your data, or perhaps the filing system for a vast library. Just as a library can organize its books alphabetically, by genre, or by publication date, a data model dictates how your application sees and interacts with the information it processes. Why are data models so important? Because the choice of data model profoundly impacts every aspect of your application. How easily you can develop features, how quickly your application performs, and crucially, how well it can scale and remain reliable. Different data models are optimized for different use cases and different kinds of operations. Choosing the right one or combination of them is a critical design decision. Let's explore the landscape of data models, starting with the long-standing king and then venturing into the more recent contenders. 3.1. The Grand Old King. The relational model. For decades, the undisputed champion of data storage has been the relational model. Developed in the 1970s, it's the foundation of well-known databases like MySQL, PostgreSQL, Oracle, and SQL Server. Its core concept is beautifully simple. Data is organized into tables, which resemble spreadsheets. Each table has a fixed set of columns, like headers in a spreadsheet, that define the attributes, and rows, like individual lines in a spreadsheet, represent individual records. For example, a table for customers might have columns for customer ID, name, email, and address. A products table might have product ID, name, price, and description. The magic of the relational model comes from how these tables can be linked together using relationships. If a customer places an order, you don't repeat all the customer's details in the order record. Instead, the orders table would simply have a customer ID column that refers back to an entry in the customer's table. This linking is done through a powerful query language called SQL, Structured Query Language, which allows you to efficiently join information from multiple tables. For instance, you could ask, "Show me the name and email of every customer who bought product X." SQL makes such complex queries straightforward. Strengths of the relational model: strong consistency. Relational databases are known for their commitment to data integrity. They provide ACID properties, atomicity, consistency, isolation, durability, which we'll explore in detail in Chapter 8. For now, understand that ACID ensures that transactions, sequences of operations, either complete entirely and correctly, or they don't happen at all, even in the event of failures. This is crucial for financial transactions, inventory management, and other systems where data accuracy is paramount. Well-established and mature. With decades of development, relational databases are incredibly robust, well understood, and come with a wealth of tools and expertise. Flexible querying. SQL is a powerful and declarative language, allowing you to ask complex questions of your data without specifying how the database should find the answer. This flexibility is a huge advantage for analytical queries or ad hoc reporting. Weaknesses of the relational model in certain contexts. Schema rigidity. Changing the structure of a relational database, e.g., adding a new column to a large table, can be a significant operation, sometimes requiring downtime. This can slow down development in rapidly evolving environments. Horizontal scalability challenges. While relational databases can scale up by running on more powerful hardware, scaling them out across many machines, horizontal scaling, for extremely high write volumes or massive datasets is notoriously complex. Joins become very difficult to perform efficiently across distributed tables. Object relational impedance mismatch. Modern applications are often built using object-oriented programming languages, translating between the object-oriented view of data, where related information is often nested within objects, and the table-based relational view can be cumbersome and require special mapping layers. Despite these limitations, the relational model remains the backbone for countless applications, especially those requiring strong transactional guarantees and complex query capabilities. 3.2 The rise of alternatives. NoSQL models. As the internet boomed in the late 2000s, traditional relational databases began to show strain under the sheer volume, velocity, and variety of data generated by web-scale applications. Companies like Google, Amazon, and Facebook, grappling with unprecedented data loads, started building their own highly scalable, distributed data stores. This movement led to the emergence of what became known as NoSQL databases. The term NoSQL initially meant no SQL, implying a rejection of SQL and the relational model. However, it's more accurately interpreted today as not only SQL, signifying a broader range of data models tailored for different challenges. The motivations behind NoSQL generally revolved around massive horizontal scalability, the ability to easily distribute data across hundreds or thousands of servers, handling enormous data volumes and very high throughput. Flexible schemas, the ability to evolve data structures more easily without complex migrations, adapting quickly to changing application requirements. High availability partition tolerance, designing systems that can continue to function even when parts of the network or individual servers fail. NoSQL isn't a single technology, but a diverse family of databases, each with its own strengths and weaknesses. Let's look at the most prominent categories. One-document databases, how they store data. Data is stored in self-contained documents, often in formats like JSON, JavaScript object notation. A document can contain nested structures, like a customer's addresses and contact numbers all within one customer document, reflecting how data is often structured in application code. Examples: MongoDB, Couchbase. Strengths: highly flexible schema. You can add new fields to documents without affecting existing ones. Excellent for representing hierarchical or nested data, good locality of reference. Retrieving a single document often gets you all the related information you need, and easy mapping to object-oriented programming languages. Weaknesses: joins are difficult or non-existent, meaning if you frequently need to combine data from different document types, you might have to do it in your application code, leading to more complex queries or data duplication. Transactions across multiple documents can also be challenging. Analogy: imagine a filing cabinet where each folder contains a complete record for a person or an item, including all their details and related sublists, rather than spreading pieces of information across many different labeled index cards. 2. Key value stores, how they store data, the simplest NoSQL model. Data is stored as a collection of unique keys, each associated with a value. The value can be anything: a string, a number, a complex object, or even an image, and the database simply stores it without understanding its content. Examples: RIDI's DynamoDB. While DynamoDB offers more, its core is key value, memcached. Strengths: extremely high performance for read and write operations, incredibly scalable, ideal for caching or storing simple configuration data, user sessions, or shopping cart contents. Weaknesses: you can only retrieve data by knowing its exact key. There are no powerful query languages for searching based on values, and no built-in relationships between different key-value pairs. Analogy: a giant dictionary. You provide a word, the key, and it gives you the definition, the value. You can't ask it to show me all the words that mean happy. 3. Column family or wide column stores. How they store data. While they use rows and columns conceptually, they are very different from relational tables. Each row can have a dynamic, highly sparse set of columns, and columns are grouped into column families. They are optimized for very large datasets and high write throughput, especially for append-only data. Examples: Apache Cassandra HBase. Strengths: extremely high write performance, excellent for time series data e.g., sensor readings, web analytics logs, very robust horizontal scalability. Weaknesses: more complex data modeling than document or key-value stores, less flexible for ad hoc queries, and lacks strong transactional capabilities across rows. Analogy: imagine a vast, infinitely wide spreadsheet where each row can independently decide which columns it wants to use, and most cells are empty. You'd typically design your queries to read entire vertical slices, column families, very quickly. 4. Graph databases. How they store data. Graph databases are specifically designed to model and query relationships between entities. Data is represented as a network of nodes, entities, like people or places, and edges, relationships between nodes, like friends with or lives in. Both nodes and edges can have properties. Examples: Neo4j, Amazon Neptune. Strengths: incredibly efficient for traversing complex relationships and performing connectedness queries, e.g., find all friends of friends up to X degrees. What is the shortest path between A and B? Ideal for social networks, recommendation engines, fraud detection, and knowledge graphs. Weaknesses: not well suited for simple record storage or aggregate queries on large datasets, and scaling graph databases horizontally can be complex depending on the query patterns. Analogy: a map of a social network where each person is a dot node and a line between them represents a friendship edge. You can easily trace connections and find groups of friends. 3.3 When to use which model. The right tool for the job. With such a diverse array of data models, the crucial question becomes, which one should you choose? The answer is almost always, it depends. There is no single best data model for all applications. The optimal choice hinges on your specific needs, particularly your data's structure, your typical query patterns, your consistency and transactional requirements, your desired scale, and your team's familiarity. Consider your data's structure. Is your data highly structured with many fixed relationships, e.g., financial transactions, inventory? A relational database might be a good fit. Is it hierarchical and ever-changing, e.g., user profiles, product catalogs with varying attributes? A document database could be better. Is it highly interconnected, e.g., social connections, routing information? A graph database excels here. Consider your query patterns. Do you need complex ad hoc queries and joins? SQL's power is unmatched. Do you primarily retrieve data by a unique identifier? A key-value store offers unparalleled speed. Are you performing deep relationship traversals? A graph database is ideal. Consider consistency requirements. Do you need strong transactional guarantees? ACID. Relational databases are built for this. Can your application tolerate eventual consistency, where data might be temporarily inconsistent but will eventually become consistent? Many NoSQL databases offer higher availability and scalability by relaxing consistency. Consider scalability needs. Are you expecting millions of requests per second and petabytes of data? The horizontal scalability of many NoSQL databases might be necessary. Developer familiarity and ecosystem. The best technology is often the one your team understands best and can troubleshoot effectively. 3.4 Evolution and polyglot persistence. The world of data models is not static. Relational databases have started to incorporate features like JSON support, blur the lines with features like columnar storage, and offer more flexible schemas. On the other hand, some NoSQL databases are adding transactional capabilities and more sophisticated querying. The boundaries are blurring. This evolution has given rise to the concept of polyglot persistence. Just as polyglot means knowing multiple languages, polyglot persistence means using multiple different data storage technologies within a single application or system. This isn't about choosing one database for your entire application, but rather selecting the most appropriate data model and database technology for each specific piece of data or workload that your application manages. For example, an e-commerce platform might use a traditional relational database for customer orders and financial transactions, where ACID properties are critical, a document database for storing product catalogs, because products have varied, evolving attributes and nested descriptions, a key value store for user sessions and caching frequently accessed data for speed and scalability, a graph database to power its recommendation engine, customers who bought X also bought Y, or friends of yours like this item, a column family store for storing user activity logs and website analytics for high write throughput and scale. Benefits of polyglot persistence: optimized performance. Each data store is chosen for its strengths, leading to better overall application performance for specific tasks. Flexibility and adaptability. You're not locked into one model, allowing your system to adapt better to new requirements. Challenges of polyglot persistence: increased complexity. Your system becomes more complex to design, build, deploy, and operate. Teams need to understand multiple database technologies. Operational overhead. Managing and monitoring multiple disparate databases adds significant operational burden. Data synchronization. Maintaining consistency of data across different stores becomes a non-trivial challenge. How do you ensure that a user ID is the same in the relational database as it is in the document store? This often involves sophisticated messaging patterns, which we will explore in later chapters. Choosing a data model is a foundational decision with long-lasting implications. It shapes how your application interacts with the world's information. Understanding the philosophical underpinnings and practical consequences of each model is the first step toward building truly data-intensive applications. In the next chapter, we'll dive deeper into how these models are actually represented under the hood of a database and how they physically store and retrieve your valuable data. Chapter 4, Under the Hood. Data storage and indexing. We've talked about data models in the previous chapter, exploring the conceptual blueprints for organizing our data. But ideas and blueprints are just the beginning. How does a database actually take that abstract data model, whether it's a row in a relational table, a JSON document, or a key value pair, and store it on physical hardware? How does it then find that data again quickly when you ask for it? This chapter pulls back the curtain, diving into the fundamental mechanisms of data storage and the magic behind fast data retrieval. Indexing. At its core, a database is a sophisticated piece of software that manages persistent storage. This means it writes data onto non-volatile memory, typically hard disks, HDDs, solid-state drives, SSDs, or increasingly networked storage. The key challenge lies in making these operations efficient, keeping in mind the reliability of the data and the scalability of the system. 4.1. The simplest storage. Append-only logs. Let's start with the most basic way to store data, an append-only log. Imagine a simple notebook where you only ever write new entries at the very end. If you want to record a new customer, you append their details to the bottom. If a customer changes their email, you don't erase the old one. You write a new entry at the bottom with the updated email and a timestamp, indicating it's the latest version for that customer. This approach, straightforward as it sounds, is remarkably powerful and forms the basis for many modern data storage systems, particularly in the realm of distributed and NoSQL databases. Advantages of append-only logs: high write throughput. Appending data is very fast. You just find the end of the file and write. This avoids the complexities of finding specific locations on disk and potentially overwriting old data, which can be slow. Durability and recovery. If the system crashes, you can recover by replaying the log from the beginning. Every change is preserved. This is a fundamental concept for reliability. Simplicity. The underlying mechanism is easy to understand and build. Disadvantages of append-only logs: read slowdowns. If you want to find a specific customer record, you have to read through the entire log from start to finish, looking for the latest entry for that customer. As the log grows, this becomes incredibly slow, making direct reads impractical for large datasets. Space consumption: you accumulate old versions of records, which can take up a lot of space. Mechanisms like compaction or garbage collection are needed to clean up old, overwritten data. Because direct reads from a simple append-only log are inefficient, databases rely heavily on additional structures to speed up retrieval. This brings us to the crucial concept of indexing. 4.2, the magic of indexing: finding your data fast. Imagine you have a massive, unindexed book and someone asks you to find every mention of data model. You'd have to read the entire book, page by page. But if the book had an index at the back, organized alphabetically, you could quickly find data model and get a list of page numbers. That's precisely what a database index does. An index is an auxiliary data structure that allows a database to quickly locate data records without having to scan the entire dataset. When you query a database for specific information, e.g., find the customer with ID 123 or find all products priced under $50, the database consults its index. How indexes work conceptually: at its core, an index maps a specific key, e.g., a customer ID, a product name, to the location of the actual data on disk. When you request data by a key that is indexed, the database first looks up the key in the index, gets the physical location, and then goes directly to that location to retrieve the data. This is much faster than scanning every record. There are various types of indexes, each optimized for different access patterns. Two of the most common and important are B-trees and log-structured merge trees, LSM trees. 4.2.1 B-trees. The go-to indexing structure. The B-tree is the most widely used indexing structure in databases, found in almost all relational databases and many NoSQL systems. It's a highly intelligent, self-balancing tree data structure that keeps data sorted and allows for efficient search, insertion, and deletion of records. Analogy: imagine a meticulously organized library where books are stored on shelves, and each shelf range has a sign telling you exactly which kind of books it contains. To find a book, you start at the main directory, the root of the B-tree, which points you to the correct aisle. That aisle then points you to the correct shelf, and so on, until you find the exact book. Each step narrows down your search dramatically. How B-trees achieve efficiency: balanced structure. B-trees are always balanced, meaning the distance from the root to any leaf node is roughly the same. This ensures that searching, inserting, or deleting any record always takes a consistently short amount of time, avoiding worst-case scenarios where one path is much longer than others. Disk-friendly. B-trees are designed with disk access in mind. Nodes within the tree are typically sized to match the disk block size, minimizing the number of times the database has to read from disk. In-place updates. When you update a record indexed by a B-tree, the database can often modify the data directly, in place, on disk. While B-trees are incredibly versatile and perform well for a wide range of workloads, they do have some characteristics. Write amplification. Updating a record can sometimes involve modifying multiple levels of the B-tree, which means more disk writes than just changing the data itself. Concurrency challenges. When many transactions are trying to modify the same B-tree at the same time, the database needs sophisticated locking mechanisms to ensure data integrity, which can become a bottleneck. 4.2.2 Log-structured merge trees, LSM trees, optimized for writes. While B-trees excel in balanced read-write scenarios, high-write throughput systems, especially many modern NoSQL databases like Apache Cassandra, HBase, and Google's Bigtable, often use an indexing and storage structure called a log-structured merge tree, LSM tree. This approach prioritizes writes and handles updates differently. Analogy: instead of updating your physical ledger on the same line, imagine you have a very fast scratchpad in memory where you jot down new entries and updates. Periodically, you take the entries from your scratchpad, sort them, and combine them into a neat, new set of pages for your main ledger on disk. Old versions of pages are simply discarded. This combines new changes with existing data in bulk, rather than making small, individual changes. How LS entries work: in memory store, memtable/SS table. All new writes are first appended to an in-memory sorted structure, often called a memtable. This is incredibly fast because it's happening in RAM. Immutability. When the in-memory store reaches a certain size, it's flushed to disk as a new, immutable, sorted file, often called a sorted string table or SS table. This file is never modified after it's written. Updates don't overwrite old data, they are simply new entries with later timestamps. Compaction. Over time, you accumulate many SS tables on disk, some containing old versions of data, some containing sparse ranges. A background process called compaction periodically merges these SS tables together, combining latest versions, discarding old ones, and reducing the number of files. This is like tidying up your ledger and throwing away the old, messy pages. Advantages of LSM trees: high write throughput. Writes are sequential appends to memory and then sequential writes to disk, which is very efficient. This leads to exceptional write performance. Good for analytics. Because SS tables are immutable sorted files, they are well suited for batch processing and analytical queries. Reduced write amplification relative to updates. While compaction does involve rewriting data, individual updates are cheap. Disadvantages of LSM trees: read amplification. When you read data, the database might have to look in several SS tables, the in-memory one, and several on disk, to find the latest version of a record. This can make reads slower than B trees, especially if compaction isn't keeping up. Compaction overhead. The compaction process consumes disk I/O, CPU, and memory resources. If it can't keep up with the incoming write load, performance can degrade. Both B trees and LSM trees are sophisticated engineering feats, each making different trade-offs to achieve particular performance characteristics. Understanding their fundamental differences helps explain why certain databases excel at certain types of workloads. 4.3 In-memory versus disk-based storage. When we talk about data storage, an important distinction is where the primary copy of the data resides. Disk-based databases. These systems primarily store their data on persistent disk storage, HDDs or SSDs. They use RAM as a cache for frequently accessed data to speed up operations, but the definitive copy is on disk. This allows them to manage datasets far larger than the amount of available RAM. Most traditional relational databases and many NoSQL databases fall into this category. In-memory databases. These systems primarily store their entire working dataset in RAM. This provides incredibly fast access times because RAM is orders of magnitude faster than disk. However, RAM is expensive and volatile. Data is lost on power loss. For persistence, in-memory databases typically write a backup copy to disk, a log or snapshot, and often replicate data to other machines to ensure reliability. They are ideal for applications requiring extremely low latency, such as financial trading platforms, real-time analytics, or high-speed caching. Examples include Redis and some specialized analytical databases, like SAP HANA. Many databases today employ hybrid approaches, selectively keeping parts of the data in memory while flushing others to disk, or using in-memory caches on top of disk-based storage. 4.4 Column-oriented storage for analytics. So far, we've implicitly considered most data to be stored in a row-oriented fashion. In a row-oriented system, like most relational or document databases, all the data for a single record, a row, or a document is stored together. For example, if you have user data with columns like user ID, name, email, country, membership tier, all these pieces of information for one user are grouped together on disk. This is efficient if you often need to retrieve all the information about a specific user. However, consider an analytical query. What is the average membership tier by country? In a row-oriented database, to answer this, you would have to read all the data for every user, then discard the name and email information, keeping only country and membership tier, and then perform the aggregation. This involves reading a lot of irrelevant data from disk, which is slow. This is where column-oriented storage shines. Instead of grouping all data for a single row together, it groups all the data for a single column together. So all user IDs are stored contiguously, all names contiguously, all emails contiguously, and so forth. Advantages of column-oriented storage: efficient for analytical queries. When you want to calculate the average membership tier by country, the database only needs to read the membership tier column and the country column from disk. It doesn't need to touch the name or email columns at all. This drastically reduces the amount of data that needs to be read, speeding up analytical workloads. Better compression. Because data within a single column is usually of the same type and often has less variation, e.g., repeating values like USA, UK, it can be compressed much more effectively than row-oriented data. This saves disk space and further reduces read times. Disadvantages of column-oriented storage: poor for transactional workloads. If your application frequently needs to read or write all the columns for a single record, e.g., retrieving a full customer profile or updating multiple fields in a transaction, column-oriented storage is much slower. Each update involves modifying multiple distinct column files. Writes can be slower. Modifying a single record means touching multiple column files, which can be inefficient compared to writing a single row. Column-oriented databases, often referred to as columnar databases or analytical databases, like Apache Parquet, a file format, Apache Kudu, ClickHouse, and some data warehouses are purpose-built for analytical processing and reporting. They often combine this storage strategy with other optimizations like vector processing, performing operations on batches of column values at once. In essence, whether your database uses B-trees or LSM trees, is disk-based or in memory, or stores data row by row or column by column, these choices are fundamental trade-offs. Each decision impacts how quickly data can be written, how fast it can be read, and the types of queries it excels at. Understanding these internal mechanisms is crucial, as they directly influence the reliability, scalability, and maintainability of the data-intensive applications you design. Next, we will explore another critical aspect of managing data: how it's represented and how its structure evolves over time. Chapter 5: Shaping Our Data, Encoding, Evolution, and Schema Changes. So far, we've explored what data-intensive applications are, the fundamental pillars of their design, and how data is conceptually modeled and physically stored. But before data can be stored, it first needs to be represented. How do we take diverse pieces of information, a person's name, their age, the date they joined a service, an image, a video, and turn them into a sequence of bytes that can be written to disk or sent across a network? This is the realm of data encoding. The choice of encoding format profoundly impacts how robust and flexible your system can be, especially when it comes to changing the structure of your data over time. In a dynamic world, applications are rarely static. Requirements change, new features are added, and the way we understand and model our data evolves. This process of adapting data structures over time, often called schema evolution, brings its own set of challenges. 5.1 Different languages for data. Encoding formats. Imagine trying to communicate a complex idea to someone without agreed-upon words or grammar. Similarly, for applications to exchange data effectively, they need a common language and structure. This is where data encoding formats come in. Broadly, they fall into two categories: human-readable text formats and more compact binary formats. 5.1.1 Text-based encoding, JSON, XML, CSV. These formats are ubiquitous, especially for data exchange over networks like web APIs and for simple file storage. JSON, JavaScript Object Notation, hugely popular due to its simplicity and readability. It represents data as key-value pairs and ordered lists, arrays. For example, a user profile might look like: userid, 42, name, Alice, email, alice@example.com, tags, developer, reader, XML, extensible markup language, older than JSON but still widely used, particularly in enterprise systems. It uses tags to define elements and attributes. CSV, comma-separated values, the simplest, often used for tabular data, but lacks explicit type information or nested structures. Advantages of text formats. Human-readable, You can open a JSON or XML file and often understand its content with a glance. This is incredibly helpful for debugging and manual inspection. Widely supported. Almost every programming language has built-in or readily available libraries for parsing and generating these formats. Schema flexibility for JSON XML. They don't inherently require a strict schema, making them easy to evolve initially. You can add new fields without breaking existing parsers, though old parsers might just ignore them. Disadvantages of text formats: verbose. They often consume more bytes than necessary because they include keys, tags, and whitespace. This means more storage space and more network bandwidth. Parsing overhead. Parsing text requires more CPU time compared to binary formats, as the parser needs to convert text representations, like 42 into an integer, and deal with character encodings. Ambiguity and data type issues. For example, is 42 a number or a string? JSON and XML don't enforce data types, leading to potential misinterpretations if not handled carefully by the application. Large numbers might also lose precision if not treated as strings. Schema enforcement or lack thereof. While flexible, the lack of a strict schema can lead to validation issues where an application expects certain fields or types, but the data does not conform. 5.1.2 Binary encoding protocol buffers, Avro, Thrift, Orc, Parquet. To overcome the verbosity and parsing overhead of text formats, various binary encoding formats have emerged. These are designed to be compact, efficient to parse, and often include strong schema definition capabilities. Protocol buffers, Protobuf, developed by Google. You define a schema in a special proto language, and then Protoc, the protocol buffer's compiler, generates code in various programming languages, Java, Python, C++, etc., to easily serialize and deserialize your data structure. Analogy: if JSON is like writing instructions in plain English, Protobuf is like creating a highly optimized, pre-agreed-upon instruction manual with specific codes for common words and actions. Apache Thrift. Developed at Facebook, now an Apache project. Similar to Protobuf in principle, with its own interface definition language, IDL, and code generation. Apache Avro, developed as part of the Hadoop ecosystem. It's unique because its schema is typically stored with the data, not just as a separate definition file. This is particularly useful for data processing pipelines where schema evolution is frequent. Orc and Parquet. Specifically designed for columnar storage, as discussed in Chapter 4, and optimized for analytical workloads, often used in conjunction with big data frameworks like Spark and Hive. Advantages of binary formats. Compact. Significantly smaller size, leading to reduced storage costs and faster network transfers. Faster parsing. Being binary, they are quicker for machines to parse, leading to lower latency and higher throughput. Strong schema enforcement. They rely on a rigorously defined schema, ensuring data types are consistent and fields are present as expected. This reduces bugs due to malformed data. Disadvantages of binary formats: not human-readable. You can't just open a binary file and understand its contents. Debugging usually requires specialized tools or deserializing the data first. Requires schema definition. Changes to data structures typically require updating the schema definition and regenerating code, which can add a step to the development workflow. 5.2 Evolving data. The challenge of schema changes. The choice of encoding format is deeply intertwined with perhaps the biggest challenge in handling data in the long run: schema evolution. As applications grow, so do their data structures. New features demand new fields, existing fields might need type changes, or entire parts of the data model might be restructured. How do you roll out these changes reliably in a system that might have data created by old versions of the software and needs to be read by new versions, or vice versa? This boils down to two critical compatibility requirements. Backward compatibility. New code can read data written by old code. This is essential when you update your software. You upgrade your application servers to the new version, but your database might still contain data written by the older version of the application. The new version must be able to understand and process that old data. Analogy. Imagine a word processor that opens documents created by an older version of itself. This is taken for granted, but it requires careful design. Forward compatibility. Old code can read data written by new code. This is typically harder to achieve and often overlooked, but it's crucial for zero downtime rolling upgrades in distributed systems. For instance, in a large cluster, you might update one server to the new version while others are still running the old version. The new server starts writing data using the new schema. If an old server then tries to read that data, it must not crash or misinterpret it. Analogy. Imagine an older version of your word processor trying to open a document created by a newer version, which might contain features it doesn't recognize. It should ideally gracefully ignore the unknown features rather than crashing. Strategies for schema evolution and their compatibility implications. Adding new fields. Backward compatible. Yes, if the old code simply ignores the new, unknown fields in the data it reads. This is generally true for JSON, XML, protobuf, thrift, and Avro if new fields are added as optional. Forward compatible. Yes, if the new fields are optional and the old code is designed to ignore unknown fields. This is why protobuf/thrift/Avro are good. They implicitly handle this. Raw JSON XML parsers often struggle as they don't have a clear notion of optional fields outside of explicit schema validation. Removing fields. Backward compatible. Yes, as the new code simply ignores the missing fields from old data. Forward compatible. No, usually not. If old code expects a field to be present and new code writes data without that field, the old code will likely crash or behave unexpectedly. A robust deprecation strategy is required, e.g., mark a field as deprecated, keep writing it for some time, then remove it only after all readers are upgraded. Renaming fields. Effectively combining adding a new field and removing an old one. This typically breaks all compatibility unless you implement a special translation layer. Changing data types, backward compatible, can be problematic. If you change a number from integer to string, old code expecting an integer will likely fail. Some systems allow limited type coercion, e.g., if a number fits in a smaller type. Forward compatible, very dangerous. Old code won't understand a new type. 5.3 Rolling out schema changes in a live system. Given these compatibility constraints, how do you actually deploy a schema change in a system with zero downtime? Consider a typical deployment scenario. Phase 1. Dual write optional but often useful. If you're renaming or changing a field, start by having the new version of your application write data in both the old and new formats. Old services still read the old format. New services start writing the new format while still accepting the old. Phase 2. Deploy new application version, backward compatible. Deploy the new version of your application code to all servers. This new code must be capable of reading both old and new data formats, a fully backward compatible system. For example, if you added a new field, the new code will preferentially read it, but if it encounters old data without the field, it will use a default value. Phase 3. Data migration, optional asynchronous. Only once all application code is updated, you can run a background process to rewrite old data into the new format, if necessary. This is especially relevant in relational databases with alter table statements or in document databases where you might need to backfill new fields. This is usually a non-blocking, gradual process. Phase 4. Remove old format support, forward compatible implications. If you want to remove support for the old format, e.g., delete an old column, you need to ensure that all parts of your system, including older services or batch jobs that might still be reading old data, have been updated to only expect the new format. This is where forward compatibility becomes paramount. If old servers were expected to read new data and you've removed an old field they relied on, you'll have problems. This multi-phase approach allows for gradual, controlled rollouts, minimizing the risk of outages. Forward compatibility is often the harder requirement because it constrains how you evolve your system. If you want truly independent microservices, each potentially running different versions, guaranteeing forward compatibility becomes a cornerstone. 5.4 Tools and strategies for data evolution. Schema definition languages, IDLS. Tools like protobuf, Thrift, and Avro provide a centralized, machine-readable way to define your data structures. This generates code that seamlessly handles serialization/deserialization and manages common evolution patterns, like adding optional fields automatically. They are often used for inter-service communication and internal data storage formats. Schema registries. In a distributed environment, keeping track of all your schemas and their versions can be complex. A schema registry, like Confluent Schema Registry for Avro, acts as a central repository for schemas, ensuring that producers and consumers of data agree on the format. Schema on read versus schema on write. Schema on write, traditional relational databases. You define the schema before you write data. Changes require schema migrations. Strong data integrity. Schema on read, many document databases, MongoDB, Couchbase. Data is written without a strict, enforced schema. The interpretation of the data structure, the schema, is applied when you read it in your application code. This provides great flexibility, but pushes the burden of validation and consistency into the application layer. It can make schema evolution seem easier, but it means dealing with messy data is now the responsibility of every piece of code that consumes it. Versioned APIs. For external communication, APIs, versioning can help manage schema changes. For example, V1 users and V2 users allow clients to migrate at their own pace. Understanding data encoding and schema evolution isn't just about syntax. It's about designing for the long life of your data and your applications. Thoughtful choices here directly contribute to the maintainability of your system by making changes less painful, and to its reliability by preventing crashes due to data mismatches. They also indirectly contribute to scalability by reducing data size and parsing overhead, freeing up resources for actual computation. As we move on, we'll explore how these carefully encoded and evolving pieces of data are spread across multiple machines to achieve higher availability and performance through replication. Chapter 6, The Art of Copying, Replication for High Availability and Performance. In the previous chapters, we've laid the groundwork for understanding data-intensive applications. We discussed the importance of reliability, scalability, and maintainability, and explored how data models shape our understanding of information, and how storage engines transform those models into persistent bytes. Now, let's confront a fundamental challenge in distributed systems. What happens when a single database server isn't enough? What if it crashes, or if the sheer volume of read requests overwhelms it? The answer lies in replication, the practice of keeping multiple copies of the same data on different machines. This isn't just about making backups, though that's a crucial byproduct. It's about fundamentally changing how we design systems to be always available and incredibly fast. 6.1 Why copy data? The core reasons. At first glance, copying data might seem redundant or inefficient. Why store the same information multiple times when storage is a finite resource? The reasons are compelling and directly address the big three pillars of system design: reliability and fault tolerance. A single server, no matter how powerful or expensive, is a single point of failure. If that server crashes due to hardware failure, software bug, or even a power outage, your application goes down and your data becomes inaccessible or even lost. Replication solves this by creating redundancy. If one replica fails, other copies can seamlessly take over, ensuring your application remains available and your data intact. Think of it like a spare tire in your car. You hope you never need it, but it offers immense peace of mind if a tire, your primary server, unexpectedly goes flat. Or imagine keeping multiple copies of an important document in different locations, so if one copy is lost, others survive. Performance and read scalability. As your application grows, the number of users and the volume of data they request can rapidly overwhelm a single server. By having multiple copies of your data, you can distribute the read workload across several machines. Instead of one server handling all read requests, e.g., showing a Twitter feed or retrieving a product page, multiple servers can share the burden, accelerating response times. Furthermore, strategically placing replicas closer to geographically distributed users can significantly reduce read latency. A user in Europe querying a database in the US will experience higher latency than if a replica is available locally. Replication brings the data closer to the user, like having branch libraries instead of just one central one. Offline operations and analytics. Many analytical tasks, like generating complex reports or running machine learning models, can be very resource-intensive, consuming significant CPU, memory, and disk I/O. Running these queries directly on your primary transactional database could severely impact its performance, slowing down customer-facing operations. By replicating data, you can dedicate one or more replicas specifically for analytical workloads. This separation of concerns ensures that heavy analytical queries don't interfere with the smooth operation of your live application. Replication is a fundamental technique for achieving high availability and scalability in data-intensive applications. However, different replication strategies make different trade-offs, particularly concerning consistency and performance. 6.2 Replication approaches. Leader-follower, aka master-slave. The most common and perhaps easiest to understand replication method is the leader-follower model. In this setup, one replica is designated as the leader, sometimes called the master or primary. All database write operations, inserts, updates, deletes, must go to the leader. All other replicas are followers, sometimes called slaves or replicas or secondaries. They receive a stream of changes, often a log of write operations, from the leader and apply these changes to their local copies of the data. Read operations can typically be handled by either the leader or any of the followers. How does it work? When the leader receives a write operation, it first processes and stores the change locally. Then, it sends a notification or a log of that change to all connected followers. The followers then apply this change to their own datasets. This ensures that the data eventually becomes consistent across all replicas. Advantages: write consistency. Since all writes go through a single leader, it's relatively straightforward to ensure that all changes are applied in a consistent order, avoiding simple conflicts where two writes might try to modify the same data concurrently. Read scalability. By distributing read requests across multiple followers, you can scale the number of reads your system can handle significantly beyond what a single server could manage. Disadvantages: leader as a single point of failure for writes. If the leader node fails, no new writes can be processed until a new leader is elected or manually promoted. This failover process can be complex. Choosing a new leader requires agreement among the remaining nodes, and there's a risk of data loss if the failed leader had processed some writes that hadn't yet been fully replicated to followers. Replication lag. Changes applied to the leader don't instantly appear on the followers. There's always a delay, known as replication lag. This can lead to eventual consistency, a concept we'll explore in detail shortly. Synchronous versus asynchronous replication. The way the leader communicates with its followers defines two key variations. Synchronous replication. The leader waits for at least one follower to confirm that it has successfully received and applied the write operation before acknowledging the write to the client. Pro guarantees data durability. Data is safely on multiple distinct nodes. It also allows for read-your-own writes, consistency from any up. Chapter 7, Dividing by Conquest. Partitioning data for scale. In the previous chapter, we explored replication as a powerful technique to enhance reliability and improve read scalability. By making copies of your data, you can safeguard against failures and distribute the burden of read requests across multiple machines. However, while replication is excellent for read-heavy workloads, it often doesn't solve the problem of overwhelming a single node with write operations. Every write still needs to be processed by the leader in a leader-follower setup or coordinated among a few designated nodes. What happens when your application's write volume, or the sheer size of the dataset, exceeds the capacity of even the most powerful single server? This is where partitioning, also known as sharding, comes into play. Partitioning is the process of breaking a large dataset down into smaller, more manageable subsets, and distributing these subsets across multiple different machines, each operating independently. Instead of one massive database, you have several smaller, interconnected databases, each responsible for a distinct slice of your total data. 7.1 the necessity of horizontal scaling. Even with replication, a single leader node still bottlenecks write scalability. Imagine a popular social media platform. Millions of new posts, comments, and likes flow in every second. A single server, no matter how optimized, would eventually be unable to handle this immense inbound write traffic. Similarly, if your entire dataset grows to hundreds of terabytes or petabytes, even a single-node database would struggle with disk I/O, memory management, and backups. Partitioning offers the solution: horizontal scalability. It allows us to scale beyond the limits of a single machine by adding more machines to the cluster. This divides the workload and data storage across many commodity servers, offering potentially limitless scalability. Each machine is responsible for only a fraction of the total data and traffic, making its individual task much more manageable. 7.2 Approaches to partitioning. How to divide your data. The fundamental question in partitioning is, how do you decide which piece of data goes to which machine? There are several common strategies, each with its own advantages and trade-offs. 7.2.1 Partitioning by key range, range-based partitioning. This approach works by assigning a range of keys to each partition. For example, if you have a database of users, you might decide to store users whose IDs, or names, fall alphabetically between A and M on one server, and users between N and Z on another. More realistically, you might partition by postal code, date, or a product category. How it works. Each partition is responsible for a contiguous range of keys. A dedicated service or a lookup table knows which range belongs to which server, sometimes called a directory service or config server. Analogy. Imagine a very large library where books are organized by the first letter of the author's last name. All authors AM are in one building, NZ in another. Strengths. Easy range queries. If you want to find all customers whose names start with B, you know exactly which partition to query. This is very efficient for scanning through a range of data. Good locality. Related data, e.g., all posts from a particular month, are likely to be stored together on the same partition. Weaknesses. Hot spots, uneven load distribution. If your chosen partitioning key doesn't distribute the load evenly, some partitions can become hot, receiving significantly more traffic or data than others. For example, if you partition by date, and most new data is being written yesterday today, those partitions will take a disproportionate load. Or, if a service goes viral and many users have names starting with the same letter, that partition might become overloaded. Manual intervention. Identifying hotspots and rebalancing them often requires human intervention or careful planning. 7.2.2 Partitioning by hash of key, hash-based partitioning. To address the problem of hotspots in range partitioning, hash-based partitioning offers a solution. Instead of relying on the key's inherent order, we apply a hash function to the key, and the resulting hash value determines which partition the data belongs to. How it works. A hash function takes an input, your partition key, e.g., a user ID, and generates a seemingly random, fixed-size number. This number is then typically used to assign the data to one of n partitions, e.g., hash key modulo n. Analogy. Imagine a large mail sorting facility. Instead of sorting mail alphabetically, clerks calculate a number based on the recipient's name using a secret formula, and that number tells them exactly which of the hundreds of bins to put the letter into. This spreads the mail evenly. Strengths. Even distribution. Hash functions are designed to produce a uniform distribution of values, which in turn leads to a more even distribution of data and load across partitions. This effectively mitigates the hotspot problem for write-heavy workloads. Simple load spreading. When new nodes are added, only a small percentage of existing data needs to be moved using techniques like consistent hashing. Weaknesses. Loss of range query efficiency. Because related keys are randomly scattered across partitions based on their hash values, finding data within a specific range, e.g., all users who signed up last month, requires querying all partitions, which can be very inefficient. Unpredictable data locality. Data that you might naturally want to access together might end up on different partitions. 7.3 Key challenges in partitioning. While partitioning is essential for horizontal scalability, it introduces a new set of complexities that require careful architectural consideration. 7.3.1 Rebalancing partitions. What happens when your data grows beyond the capacity of your current partitions, or when you add new servers to your cluster? You need a way to rebalance the data moving partitions, or parts of them, from overloaded machines to less utilized ones or newly added nodes. When to rebalance? Data growth. As your dataset grows, existing partitions might become too full. Uneven load. A hot spot might emerge that needs to be split and redistributed. Hardware failure. If a server fails, its partitions need to be moved to healthy servers. Removing nodes. When you add new capacity, you want to redistribute data and load to utilize it. How it works. Rebalancing typically involves a background process that copies data from overloaded partitions to new, empty ones. During this process, the system must continue to serve requests, which adds complexity. It often involves temporarily routing requests for the moving data to the old node while the data is copied, then switching them over to the new node once the copy is complete. Trade-offs. Rebalancing can consume significant network bandwidth and I/O resources, potentially impacting the performance of live queries. Careful planning is needed to ensure rebalancing doesn't cause an outage or degrade service. Many systems feature automatic rebalancing, but even then, careful monitoring is crucial. 7.3.2 Hotspots and mitigation. Regardless of the partitioning strategy, a disproportionate amount of read or write traffic to a single partition is a hot spot and can lead to performance bottlenecks. Causes: unwise partitioning key, e.g., partitioning by create date when all new writes happen on the current day's partition. Superuser effect. A single user, e.g., a celebrity on a social media site, generates millions of reads or writes, concentrating traffic on their partition. Mitigation. Choose a better partitioning key. Select a key that inherently distributes load more evenly. Salt hotkeys. For hash partitioning, if a specific key is known to be hot, you can add a random prefix or suffix, a salt, to it before hashing. This spreads the data for that hot key across multiple partitions, ensuring that individual operations, like updating that one key, are still distributed. Reading all data for that key would then require querying multiple partitions, but it solves the hot spot issue for writes. Subpartitioning hot ranges. For range partitioning, if a range becomes hot, it can be split into smaller subranges, and each subrange can be moved to its own dedicated machine. 7.3.3 Distributed queries across partitions. One of the biggest complexities introduced by partitioning is the difficulty of executing queries that span multiple partitions. Distributed join operations. If you need to join data from two different tables, and those tables are partitioned differently, or even if they're partitioned by the same key but the necessary data is on different machines, the database has to perform a distributed join. This usually means moving a lot of data across the network between different partition machines, which is slow and expensive. Distributed aggregations. Similarly, if you want to calculate an aggregate, like a sum or average over your entire dataset, select AVG, value from table, and the data is spread across many partitions, the database has to send the aggregation query to all partitions. Each partition computes a local aggregate for its slice of the data. All partial aggregates are sent to a central coordinator. The coordinator combines the partial results into a final global aggregate. This scatter-gather approach works, but it's much slower than a single-node aggregation. Cross-partition transactions. Ensuring atomicity and consistency when a single transaction needs to modify data on multiple partitions is extremely complex. This requires mechanisms like two-phase commit, 2PC, which we will discuss in depth in the next chapter. Many distributed databases explicitly avoid supporting full cross-partition transactions to simplify their architecture and improve performance, instead relying on application-level eventual consistency or saga patterns. 7.4 Choosing the right partitioning key. The choice of partitioning key, also known as a shard key or primary key, is arguably the most critical decision in designing a partition system. It dictates how your data is distributed and how well your system can scale and perform for various query patterns. A good partitioning key should distribute load evenly, prevent hotspots, and ensure that data and query traffic are spread uniformly across partitions. Support common query patterns. Allow frequent queries to be routed to a single partition, minimizing expensive cross-partition operations. Minimize cross-partition operations. If significant joins or aggregations are needed, try to co-locate related data on the same partition, e.g., if you often query user data and their orders together, make sure they are on the same partition. For example, a common trade-off is between using a unique user ID, good for even distribution, but might not support range queries, versus a geographical region, good for localized queries, but could create hot spots if one region is very active. Partitioning is a powerful architectural decision that enables systems to handle truly massive datasets and extreme loads. However, this power comes at the cost of increased complexity. It's a classic example of the trade-offs inherent in distributed systems design. Sacrificing some simplicity and ease of global data management to gain unprecedented levels of write scalability and availability. Understanding these trade-offs is essential for building robust and future-proof data-intensive applications. In the next chapter, we'll delve deeper into the intricate world of transactions and how we manage data integrity, especially in these increasingly distributed environments. Chapter 8, The Illusion of Atomicity, Transactions for Data Integrity. In the world of data-intensive applications, accuracy and reliability are paramount. Whether you're managing financial transactions, tracking inventory, or delivering crucial healthcare information, you need to be absolutely sure that your data remains consistent and correct. This is where the concept of a transaction becomes indispensable. At its core, a database transaction is a sequence of operations performed as a single logical unit of work. Think of it like a theatrical play with a distinct beginning and end. All the actions within that play must either succeed together as a complete story, or they must fail entirely, leaving no trace of their attempt. There's no in-between, no partial success. Imagine a bank transfer. You want to move money from account A to account B. This involves two steps: deducting money from account A, adding money to account B. What if the system crashes right after step 1, but before step 2 completes? Account A has less money, but account B hasn't received it. Money has simply vanished. This is an unacceptable situation. A transaction ensures that either both steps complete successfully, or if anything goes wrong, neither step has any lasting effect, and the money remains in account A. This all-or-nothing guarantee is critical for maintaining data integrity. 8.1 Acid Properties, the gold standard. The bank transfer example highlights the need for a transaction to possess certain properties, commonly summarized by the acronym ACID. Atomicity. This is the all-or-nothing property. A transaction is treated as a single, indivisible unit. If any part of the transaction fails, the entire transaction is rolled back, leaving the database in its state before the transaction began. It's like an atomic reaction. It either happens completely or not at all. You can't have half a bank transfer. Consistency. A transaction brings the database from one valid state to another valid state. This means that a transaction should never violate any defined rules or constraints within the database. For instance, an account balance should never drop below 0, or a unique identifier must remain unique. It's crucial to understand that database consistency here refers to the database's internal constraints, like unique keys, foreign key relationships. Application-level consistency, e.g., the total sum of money in all accounts must remain constant, is the responsibility of the application logic and transaction design. Isolation, when multiple transactions are running concurrently. At the same time, the isolation property ensures that each transaction appears to execute independently, as if it were the only transaction running. The intermediate states of one transaction are not visible to other concurrent transactions. If Alice and Bob both try to transfer money at the exact same moment, neither transaction should interfere with the other, nor should they see each other's incomplete operations. They proceed as if they were running one after the other. Durability. Once a transaction has been successfully committed, meaning it's completed and its changes have been applied, its changes are permanent. They will survive even in the event of system failures, power outages, or crashes. The database guarantees that once it tells you a transaction is committed, that data is safely written to non-volatile storage and won't be lost. Traditional single-node relational databases have spent decades perfecting the implementation of these ACID properties, making them incredibly reliable for managing data integrity. 8.2 Concurrency Control. Ensuring isolation. The challenge of isolation becomes particularly complex when multiple users or processes are trying to read and write the same data simultaneously. Without proper controls, concurrent transactions can lead to various anomalies. Lost updates. Two transactions read the same data, both modify it, and then both write it back. One transaction's update might overwrite the others, effectively losing one of the changes. Example: two people simultaneously adding an item to the same inventory count. Dirty reads. One transaction reads data that has been written by another transaction, but that second transaction hasn't committed yet. It might still fail and roll back. If the second transaction then rolls back, the first transaction has read dirty data that never actually became permanent. Non-repeatable reads. A transaction reads a piece of data twice, but between the two reads, another transaction modifies and commits that data. The two reads yield different results within the same transaction. Phantom reads. A transaction runs a query that returns a set of rows. Another transaction then adds or deletes rows that affect the scope of the first query. When the first transaction reruns its query, it gets a different number of rows. Phantoms appear or disappear. To prevent these anomalies, databases employ concurrency control mechanisms, primarily using locks. When a transaction accesses a piece of data, it might acquire a lock on it, preventing other transactions from modifying it or even reading it, depending on the lock type, until the first transaction completes. Databases offer different isolation levels, which are a compromise between strict serializability and performance. Serializable, the strongest isolation level. It guarantees that the results of running concurrent transactions are exactly the same as if each transaction had run completely, one after the other, in some sequential order. This is the goal of true ACID isolation. Achieving this often involves techniques like two-phase locking, where transactions acquire all necessary locks, then release them after completing, or optimistic concurrency control, where transactions proceed without locks but validate changes before committing. Serializable isolation is the safest but usually the slowest. Snapshot isolation, repeatable read, a very popular and practical isolation level. Each transaction reads data from a consistent snapshot of the database at the time the transaction started. Updates made by other concurrent transactions are not visible until they commit, and even then, your transaction continues to see its original snapshot until it commits. This prevents dirty and non-repeatable reads. However, it can still suffer from an anomaly called write skew, where two transactions read the same data, make decisions based on it, and then write conflicting changes that would have been prevented under serializability. Read committed, the most common default isolation level. It guarantees that reads only see data that has been committed by other transactions, no dirty reads. However, a transaction might still see different results from two separate reads if another transaction commits changes between those reads. Non-repeatable reads and phantom reads are possible. The stronger the isolation level, the more overhead it incurs, more locking, more resource contention. So engineers often choose the weakest isolation level that still meets the application's correctness requirements. 8.3 Transactions in distributed systems. The illusion shatters. While ACID transactions are well understood and robust in single-node databases, their elegance often shatters in distributed systems. When your data is spread across multiple machines, potentially in different geographical locations, ensuring absolute atomicity, consistency, isolation, and durability for operations that span these machines becomes incredibly difficult, and in some cases, practically impossible without severe performance and availability penalties. The core culprits are the inherent unreliability of networks and the lack of a global, perfectly synchronized clock. What if a network message between two parts of a transaction is delayed or dropped? What if one machine involved in a multi-node transaction crashes in the middle? How do all participating machines agree on whether to commit or abort when communication is uncertain? 8.4 Distributed transactions. Two-phase commit 2PC. Historically, the most common protocol for achieving atomicity across multiple nodes in a distributed transaction is two-phase commit 2PC. It attempts to replicate the all-or-nothing guarantee of a single-node transaction across a network of independent participants. The 2PC protocol involves a coordinator node and several participant nodes, the actual databases or services holding the data. Phase 1, the vote prepare phase. The coordinator sends a prepare request to all participants, asking them if they are ready to commit the transaction. Each participant attempts to perform the transaction's work locally and writes all changes to a durable log. They prepare to commit. If a participant can successfully prepare, it replies yes, vote to commit. If it encounters any problem, it replies no, vote to abort. Crucially, once a participant has voted yes, it must be ready to commit the transaction regardless of subsequent failures. It cannot unilaterally abort. Phase 2, the decision commit abort phase. The coordinator collects all votes from the participants. If all participants voted yes, the coordinator sends a commit command to all participants. Each participant then makes the prepared changes permanent and releases any locks. If any participant voted no, or if the coordinator times out waiting for votes, the coordinator sends an abort command to all participants. Each participant then rolls back its prepared changes. Problems with 2PC. While 2PC provides atomicity, it comes with significant drawbacks, which is why it's largely avoided in modern, highly scalable distributed systems. Blocking coordinator death, the biggest flaw. If the coordinator fails after sending prepare requests, but before sending the final commit or abort command, the participants are left in an uncertain, prepared state. They have acquired locks and cannot release them or proceed with other operations until they hear from the coordinator. This can block parts of your database for an indefinite amount of time, leading to severe availability issues. There are complex recovery protocols, but they often require manual intervention. Performance. 2PC involves multiple network round trips and requires participants to write to durable logs in the prepare phase, adding significant latency. It's too slow for interactive, high-traffic applications. Scalability. The coordinator itself can become a bottleneck, handling messages from many participants. Network partition. If network communication breaks down, the coordinator might be unable to reach participants, leading to the same blocking problem or inconsistent states. Because of these issues, using 2PC to maintain strong global consistency across disparate services or databases is generally considered impractical for systems requiring high availability and performance. 8.5 Beyond 2PC. Embracing eventual consistency and base. The realization that full ACID transactions are too costly and fragile in large-scale distributed systems led many to reconsider the fundamental trade-offs. This gave rise to relaxing some of the ACID properties to achieve better availability and partition tolerance, often leading to eventual consistency. Eventual consistency. In an eventually consistent system, if no new updates are made to a given data item, eventually all accesses to that item will return the last updated value. This means that for a period of time after an update, different replicas, or different parts of a distributed system, might see different values for the same data item. Think of how updates to your domain name, DNS, propagate across the internet. It takes time, and during that period, some people might still be rooted to the old server while others go to the new one. This forms a part of what's sometimes called the base properties, often contrasted with ACID, particularly in discussions around NoSQL databases. Basically available. The system is generally available and responsive to requests, even if consistency isn't strictly maintained across all nodes at all times. Soft state. The state of the system can change over time, even without explicit input, eventually reaching consistency. Eventual consistency. Given a long enough period without new incoming updates, all state will converge to a consistent value. Many NoSQL databases, like Cassandra, DynamoDB, are built around eventual consistency to achieve high availability and unparalleled horizontal scalability. While they may offer some weaker forms of transaction-like behavior, e.g., atomic operations on a single record, they generally do not provide globally consistent, serializable transactions across partitions. 8.6 Compensating transactions and sagas. So, if we can't rely on 2PC for business processes that span multiple services, like an e-commerce order that involves updating inventory, charging a customer, and arranging shipping, how do we maintain data integrity? The answer often lies in compensating transactions and sagas. A saga is a sequence of local transactions, where each local transaction updates its own database and publishes an event that triggers the next step in the saga. If one step in the saga fails, you don't roll back the entire operation in a single atomic step like 2PC. Instead, you perform compensating transactions to undo the effects of previous steps. Analogy. Booking a multi-legged trip. Imagine booking a trip that involves a flight, a hotel, and a rental car. Book flight. This is a local transaction with the airline system. If successful, it commits and emits an event, flight booked. Book hotel. Triggered by flight booked event. This is a local transaction with the hotel system. If successful, it commits and emits, hotel booked. Book rental car. Triggered by hotel booked event. This is a local transaction with the car rental system. Now, what if the book rental car step fails, e.g., no cars available? With a 2PC-like approach, everything would roll back. But in a saga, the book rental car transaction aborts. A rental car booking failed event is emitted. This event triggers compensating transactions. One transaction is initiated to cancel the hotel booking. Another transaction is initiated to cancel the flight booking. Challenges with sagas. Complexity. Designing compensations requires careful thought. You need to know how to undo every possible step, and often, an undo isn't a true rollback, but rather a new, distinct business operation, e.g., canceling a flight reservation is different from pretending it never happened. Eventually consistent. Sagas do not provide strong isolation. Other parts of the system might see the intermediate states, e.g., your flight is booked, but your car isn't yet before the whole saga completes or is fully compensated. Idempotency. Compensating transactions, and indeed all services participating in a saga, must often be idempotent, meaning performing the operation multiple times has the same effect as performing it once. This helps in recovery from failures. Despite the complexity, sagas are widely used in microservices architectures and distributed business processes because they enable high availability and scalability by avoiding the costly coordination of 2PC. They accept eventual consistency for the overall process in exchange for local atomicity and better performance. Conclusion. Transactions are fundamental to data integrity. While the promise of ACID properties on a single machine is powerful, the reality of distributed systems often forces a choice. The illusion of a single, effortlessly atomic, globally consistent transaction shatters when confronted with network latency, partitions, and independent failure domains. Architects and developers must consciously decide whether the strict guarantees of traditional distributed transactions, like 2PC, are worth their high cost in terms of performance, availability, and complexity. For many modern data-intensive applications, the answer is often no. Instead, patterns like eventual consistency, composite transactions, sagas, and careful application-level design are employed, sacrificing some immediate consistency for the immense benefits of scalability and continuous availability. This trade-off is one of the most significant themes in designing data-intensive applications, and understanding it is key to building systems that truly thrive under pressure. Chapter 9. Reaching Agreement. Tackling Distributed Consensus. In our previous chapter, we grappled with the illusion of atomicity in distributed systems and saw how the once reliable ACID transactions falter when spread across multiple machines. we encountered the cumbersome two-phase commit 2PC and its infamous blocking problem. The fundamental issue boils down to this: how do multiple independent machines, communicating over unreliable networks, agree on a single decision, even when some of them might fail? This profound problem is known as distributed consensus. It's arguably one of the most challenging and critical areas in distributed systems design. If you've ever found yourself in a group project where everyone needs to agree on a course of action, even when communication is spotty or people disagree, you have an intuitive grasp of the difficulty. In a distributed system, the people are computers, and the spotty communication is the unreliable network. 9.1 The challenge of agreement in an unreliable world. Imagine a committee debating an important resolution. For the resolution to pass, everyone needs to agree. But what if some members leave the room unexpectedly, machine crashes? Some members don't hear the proposal clearly, network packet loss. Some members hear different versions of the proposal, network delay or corruption. Some members take a very long time to respond, network latency. In such a chaotic environment, how can the committee ever be sure it has reached a unanimous, correct decision? This is the essence of distributed consensus. The objective of a consensus algorithm is to ensure that all non-failing nodes in a distributed system agree on a single value, even in the presence of failures, node crashes, network partitions, message loss. Critically, a consensus algorithm must achieve three things: agreement, all non-failing nodes eventually agree on the same value; validity, the agreed-upon value was actually proposed by one of the nodes; termination, all non-failing nodes eventually reach a decision, they don't wait forever. A famous theoretical result, the FLP impossibility theorem, states that in an asynchronous distributed system, where messages can be arbitrarily delayed, which includes the internet, it's impossible to guarantee consensus if even a single node can crash. This theorem highlights just how difficult the problem is and why real-world consensus algorithms must make certain assumptions, e.g., that crashes are detectable, or that a majority of nodes will remain healthy. 9.2 What problems does consensus solve? While achieving consensus is hard, it's a foundational building block for many critical functions in distributed systems. Leader election. Many distributed systems operate under a leader-follower model, as discussed in Chapter 6. If the current leader fails, the remaining nodes need to agree on a new leader. Without consensus, different nodes might pick different leaders, leading to chaos. Consensus algorithms provide a reliable way to elect a single, authoritative leader. Atomic commits. While 2PC has flaws, some distributed databases need atomic commits that go beyond what simple eventual consistency offers. Consensus algorithms can be used as a more robust mechanism to ensure that a set of changes are either committed by all participants or aborted by all, even if the coordinator fails. Distributed locks. In a distributed application, you often need to ensure that only one process can access a shared resource or perform a critical operation at a time. A distributed lock, implemented using consensus, can guarantee this mutual exclusion. Configuration management. Critical system configurations, e.g., which servers are active, database schema versions, service discovery information, must be consistent across all nodes. Consensus algorithms underpin systems that reliably store and distribute this configuration. Total order broadcast. This is a powerful primitive where messages are delivered to all participating nodes in the exact same order. This is surprisingly useful for many applications, allowing them to process events systematically and deterministically. 9.3 Consensus algorithms, Paxos and Raft. Over the years, several algorithms have been developed to tackle distributed consensus, each with its own intricacies. Paxos, developed by Leslie Lamport, Paxos is the most famous family of consensus algorithms. It's renowned for its theoretical correctness and fault tolerance. However, Paxos is also famously complex and difficult to understand, implement, and debug. Lamport himself wryly noted, "The problem with Paxos is that few people understand it." While many systems are Paxos-like or use derivatives in production, it's rare to find a direct, pure implementation. For our purposes, It's important to know that Paxos exists and is the academic gold standard, but its complexity makes it less suitable for practical discussion in a general overview. Raft. Recognizing the difficulty of Paxos, the Raft consensus algorithm was designed with a primary goal: understandability. While still complex, Raft aims to be much easier to grasp and implement correctly than Paxos, without sacrificing correctness or fault tolerance. Many modern systems, like etc., a distributed key-value store extensively used in Kubernetes, employ Raft. Raft achieves consensus by breaking the problem into 3 subproblems. Leader election. In Raft, at any given time, one node is the leader, and the others are followers. If connections are good, the leader sends regular, heartbeat messages to followers. If a follower stops receiving heartbeats, it assumes the leader has failed and starts a new election. Nodes vote for candidates, and the candidate with a majority of votes becomes the new leader. This ensures only one leader exists at a time, preventing split-brain scenarios where 2 nodes believe they are the leader, leading to inconsistencies. Analogy: a classroom needs a leader to write on the whiteboard. If the current leader goes silent, everyone waits a random amount of time. The first one to shout, "I'm running for leader," and get a majority of classmates to agree, wins. Then they start writing. Log replication. The elected leader is responsible for accepting all client requests, e.g., a write operation to a distributed log, and replicating them to all followers. When a client sends a write, the leader appends it to its own internal log, and then sends append entries messages to its followers. A write is considered committed only when the leader has successfully replicated it to a majority of its followers and received acknowledgements. This strategy, sometimes called quorum-based replication, is key to Raft's fault tolerance. Even if some followers fail, as long as a majority are healthy, the system can make progress. Analogy: the class leader writes things into a shared notebook, the log. They don't just write it on their own, they must get at least half the class to copy it into their notebooks before moving on. This way, if the leader or some students forget their notebook, a majority still has the correct, shared history. Safety. Raft has strict rules to ensure that all decisions are consistent and durable. For instance, a leader can only commit entries that are present in a majority of logs. This prevents a leader from committing an entry that might be lost if it fails. Raft's design prioritizes understanding and implementation simplicity while still providing the strong fault tolerance needed for robust distributed systems. 9.4 Total Order Broadcast. One of the most powerful applications of consensus algorithms is achieving total order broadcast, sometimes called a distributed log or atomic broadcast. Imagine a scenario where multiple clients are trying to send messages to a group of servers. Some messages might arrive at different servers in different orders due to network delays. Total order broadcast ensures that atomicity. If a message is delivered to one server, it will eventually be delivered to all non-failing servers. Total order. All messages are delivered to all servers in exactly the same order. This is incredibly useful. For example, if you build a database on top of a total order broadcast, every write operation can be treated as a message. If everyone processes the messages in the same order, starting from the same initial state, they will all end up with the exact same database state. This is how many distributed databases and streaming platforms, like Apache Kafka, achieve consistency and fault tolerance internally. Kafka, for instance, uses a form of Raft or its own ZAB-like protocol in older versions via Zookeeper to manage the metadata and leader election for its distributed commit log, ensuring messages are ordered reliably. 9.5 Practical applications in the wild. Consensus algorithms, directly or indirectly, underpin many of the distributed systems you encounter every day. Apache Zookeeper, a widely used distributed coordination service that provides a consistent, hierarchical namespace, like a file system, for configuration, naming, distributed synchronization locks, and group services. It uses an algorithm derived from Paxos called ZAB, Zookeeper Atomic Broadcast, to achieve consensus. Etc. Similar to Zookeeper, Etc. is a distributed key-value store often used for critical data, configuration, and service discovery in modern container orchestration systems like Kubernetes. It uses the Raft algorithm. Distributed databases. Many distributed databases use consensus internally for critical operations like leader election for certain partitions, managing metadata, or coordinating the distributed transaction protocol, though often not two PC-style global transactions. Google's Spanner, for example, uses a highly optimized variant of Paxos for its globally consistent transactions. Apache Kafka. While often thought of as a messaging system, Kafka relies on Zookeeper, or increasingly, its own Raft implementation called Kafka Raft for critical cluster coordination, leader election for topics, and ensuring metadata consistency. Conclusion: the cost of agreement. Distributed consensus provides a powerful guarantee. A group of machines can collectively agree on a single outcome, even amidst chaos. This is fundamental for building highly reliable and consistent distributed systems. However, this power comes at a significant cost. Consensus algorithms introduce latency. They require multiple rounds of communication between nodes, adding to the time it takes to reach a decision. Reduce availability. To guarantee consistency, many consensus algorithms require a majority of nodes to be healthy and communicating. If a sufficient number of nodes fail or are partitioned from the majority, the system might block and be unable to make progress until the network heals or nodes recover. This is a direct consequence of the CAP theorem, consistency, availability, partition tolerance, which suggests you can't have all three simultaneously in the face of a network partition. Consensus algorithms typically emphasize consistency over full availability during a partition. Increase complexity. Implementing and operating systems that rely on consensus is inherently complex and requires deep expertise. Therefore, while essential for critical core functions like leader election and metadata management, consensus algorithms are not typically used for every single data write in a high-throughput, low-latency application. Instead, they are reserved for the core infrastructure that enables the larger system to operate reliably. Understanding when and why to employ consensus and the trade-offs it entails is a hallmark of designing truly fault-tolerant, data-intensive applications. Chapter 10, Batch Processing, when data sits still. So far, we've largely focused on processing individual pieces of data, records being written, updated, or read in real time by an application. We've talked about how to store this data reliably, scale its access, and ensure its integrity. But what about when you have vast quantities of data that you don't need to process instantaneously, but rather periodically? For analyzing historical trends, generating reports, cleaning up messy datasets, or transforming data for other systems, a different paradigm often surfaces: batch processing. Batch processing is a method of executing a series of jobs or transactions together as a single group or batch, rather than one by one. Imagine collecting all your invoices for the month and processing them all at once at the end of the month, instead of processing each one as soon as it arrives. This is the essence of batch processing. Data is collected over time, then run through a process in a large chunk. 10.1 The paradigm of batch processing. Batch processing is not new. It predates real-time processing and even personal computers. Mainframes have been doing batch jobs for decades. What makes it relevant in the context of modern data-intensive applications is the sheer scale and complexity of the data involved today. Traditional batch processing might have involved sorting text files on tapes. Modern batch processing involves crunching petabytes of data distributed across thousands of machines. Key characteristics of batch processing. Periodicity. Batch jobs run on a schedule, e.g., nightly, weekly, monthly, or in response to a triggered event, e.g., once a large file arrives. Large volumes. They are designed to handle and process immense datasets, often historical archives. Efficiency over latency. The primary goal is to process the data efficiently and correctly, not to respond in real time. A job might run for hours or even days. Completeness. They usually process a complete set of data, like an entire month's worth of logs from start to finish. Predictable workloads. Typically run during off-peak hours to minimize impact on real-time systems. Use cases for batch processing. generating daily, weekly reports, summarizing sales, website traffic, or user engagement. Data warehousing (ETL), extracting data from operational systems, transforming it into a clean, consistent format, and loading it into a data warehouse for analysis, extract, transform, load. Machine learning model training. Training complex AI models often requires huge datasets processed offline. Data cleansing and deduplication, removing redundant or incorrect entries from large datasets. Billing and payroll systems, calculations often performed on a periodic batch basis. Search index building, rebuilding search indexes for large datasets that don't need instant updates. 10.2 Hadoop MapReduce. The grand vision. The explosion of big data in the early 21st century brought batch processing into the spotlight with Google's innovations and the subsequent open-source implementation, Apache Hadoop. Hadoop revolutionized how large-scale batch processing was done by introducing two core concepts. HDFS, Hadoop Distributed File System, a distributed file system designed to store very large files reliably across a cluster of commodity servers. It replicates data blocks across multiple machines to provide fault tolerance. Analogy: instead of storing a giant book on one shelf, you tear it into chapters and store each chapter on several different shelves in multiple locations. If one shelf collapses, the other copy of the chapter is still there. MapReduce, a programming model and processing framework for distributed batch computation on top of HDFS. It simplifies the parallel processing of large datasets by breaking down complex problems into two main phases. Map phase. The input data, often residing on HDFS, is divided into independent chunks. A mapper function is applied to each chunk independently. The mapper processes the input and produces a set of key-value pairs. Analogy: you have a gigantic pile of documents, your data. For the map phase, you distribute these documents among many assistants. Each assistant mapper goes through their assigned documents and identifies specific items, e.g., words, and counts their occurrences, key-value pairs like Apple. 1. Each assistant works in parallel. Reduce phase. The key-value pairs generated by all the mappers are shuffled and sorted so that all values for a given key are grouped together. These grouped values are then sent to a reducer function. The reducer aggregates or combines these values to produce a final result. Analogy: all the key-value pairs, e.g., Apple, 1 from assistant 1, Apple, 1 from assistant 5 are gathered. All counts for Apple are sent to one designated assistant reducer who sums them up, Apple, 7. All counts for banana go to another, and so on. Strengths of MapReduce: scalability. Designed from the ground up for massive horizontal scalability across thousands of nodes. Fault tolerance. If a mapper or reducer node fails, MapReduce automatically reassigns its work to another node, ensuring the job completes. Simplicity of programming model for certain tasks. For tasks that fit the MapReduce pattern, it significantly abstracts away the complexities of distributed parallel programming. Weaknesses and evolution beyond MapReduce. Not a general-purpose computing model. While powerful, many algorithms don't fit naturally into the MapReduce structure. Multi-stage algorithms, iterative graph processing, or interactive queries were awkward. High latency. Each MapReduce job involves writing intermediate results to disk between the map and reduce phases, making it very slow for workloads that chain multiple jobs together. This disk-bound nature limited its use for faster, interactive analysis. These limitations led to the development of new, more flexible, and faster batch processing engines. 10.3 Modern batch processing engines. Spark and Flink, the successors to MapReduce and now widely adopted, include Apache Spark and Apache Flink. They aim to address MapReduce's shortcomings by offering more flexible programming models and, crucially, by performing intermediate computations in memory whenever possible. Apache Spark became hugely popular for its ability to perform fast, general-purpose distributed data processing. Spark introduces the concept of resilient distributed datasets, RDDS, which are immutable, fault-tolerant, distributed collections of data that can be processed in parallel. It supports functional programming paradigms and allows more complex multi-stage data transformations without constantly writing to disk. Spark's core engine is complemented by modules for SQL queries, Spark SQL, stream processing, Spark streaming, machine learning, mlib, and graph processing, GraphX. Analogy: instead of having your assistants constantly writing partial results to disk and passing them around, they keep things on their scratchpads in memory and can easily pass those in-memory results to the next group of assistants or process them themselves in a continuous flow. Apache Flink. While Spark emerged as a general-purpose processor that also had a streaming component, Flink was designed from the ground up as a stream processing engine that can also do batch processing. It treats batch processing as a special case of stream processing, bounded streams. Flink emphasizes event-time processing, stateful computations, and fault tolerance for long-running operations. Its batch processing capabilities are very robust due to its streaming lineage. Both Spark and Flink offer in-memory processing, minimizes disk I/O, leading to significantly faster execution than traditional MapReduce. Flexible APIs support a wider range of algorithms and data transformations beyond simple MapReduce. Unified batch and stream processing, especially true for Flink and increasingly for Spark structured streaming, a single framework can handle both historical batch analysis and real-time event streams, simplifying architecture. Advanced optimization. Sophisticated query optimizers analyze your data transformations and generate highly efficient execution plans. 10.4 ETL processes and data warehousing. Batch processing is perhaps most prominently seen in ETL extract, transform, load processes, which are the backbone of data warehousing. Data warehouses. These are specialized databases designed for analytical queries on historical data. Unlike operational databases, which are optimized for quick, concurrent transactional reads and writes, data warehouses are optimized for complex, analytical queries that might scan massive tables. They typically aggregate data from many different operational sources: CRMS, ERPS, weblogs, etc. The ETL pipeline. Extract. Data is extracted from various source systems, operational databases, SaaS applications, flat files, etc. This often happens on a scheduled basis. Transform. The extracted data is cleaned, validated, normalized, and converted into a consistent format suitable for the data warehouse. This might involve removing duplicates or incorrect entries, standardizing formats, e.g., all dates in ISO format, aggregating data, e.g., summing up daily sales per product, joining data from different sources, handling missing values. Load. The transformed data is then loaded into the data warehouse tables. This load can be a full refresh or an incremental update. Modern ETL processes leverage tools like Spark, Flink, and dedicated data pipeline orchestrators, e.g., Apache Airflow, to manage these complex, multi-stage batch jobs. 10.5 Workflow management and orchestration. As batch processes become more numerous and complex, managing their dependencies and scheduling them correctly becomes a challenge. You might have job A that depends on the output of job B, which in turn depends on job C finishing successfully. Workflow management systems, or orchestrators, like Apache Airflow, Luigi, and Prefect, are used to define, schedule, and monitor these complex data pipelines. They allow you to define task dependencies, a directed acyclic graph or DAG, schedule tasks to run at specific times or intervals, monitor job status and trigger alerts on failure, retries failed tasks gracefully, backfill historical data after a change in logic. Batch processing, though not always as flashy as real-time stream processing, remains a cornerstone of data-intensive applications. It's the workhorse that cleans, aggregates, and transforms vast quantities of historical data, making it ready for deep analysis, machine learning, and strategic business decisions. It's an essential component of the data ecosystem, providing insights that real-time systems often cannot. In the next chapter, we'll pivot to the other end of the spectrum, processing data as it arrives in real time. Chapter 11. Stream processing, data in motion. In the previous chapter, we explored batch processing, where data is collected and processed in large chunks, often on a schedule. This approach is excellent for historical analysis, reporting, and building data warehouses. However, many modern applications demand immediate insights and real-time responsiveness. Think of fraud detection systems that need to flag suspicious transactions instantly, social media feeds that update within seconds of a post, or monitoring systems that alert engineers to anomalies as they happen. In these scenarios, waiting for a batch job to run hours later is simply not an option. This is where stream processing comes into its own. Stream processing is the continuous processing of data as it is generated and arrives, rather than waiting for large batches to accumulate. It treats data as an unending flow, a continuous stream of events that need to be acted upon immediately. 11.1 The need for real-time analytics and reactivity. The shift towards stream processing is driven by several key needs. Real-time insights. Businesses want to react to events as they happen. For example, an e-commerce site wants to know immediately if a product is selling exceptionally well or poorly to adjust pricing or promotions. Operational monitoring. Systems need to detect anomalies, security breaches, or system failures instantly to prevent larger issues. An IoT sensor sending temperature readings needs to trigger an alert immediately if a threshold is crossed. Personalization and recommendations. Users expect highly personalized experiences. A streaming service might adapt its recommendations based on what you are watching right now. Fraud detection. In financial services, catching fraudulent transactions in milliseconds can save millions. Customer experience. Websites might adjust their content or offer pop-ups based on a user's real-time browsing behavior. These use cases fundamentally require processing, data in motion, rather than data at rest. 11.2 Defining data streams and events. At the heart of stream processing are data streams. A data stream is an unbounded, continuous, and potentially endless sequence of events. Each event represents a discrete, atomic piece of information that occurred at a specific point in time. Events can be anything from a user clicking on a website, a temperature sensor sending a reading, a financial transaction being initiated, a log line from a server, or a customer service call starting. Characteristics of an event. Immutability. Once an event occurs, it cannot be changed. It's a factual record of what happened. Timestamp. Every event typically has a timestamp indicating when it occurred. This is crucial for ordering and processing. Schema, implicit or explicit. Events usually have a defined structure, even if it's just a JSON blob. Think of a stream of events like a never-ending conveyor belt, where new items, events, are continually being added. Stream processing systems grab items off this belt, process them, and potentially put new items back onto another belt for subsequent processing. 11.3 Stream processing models and paradigms. Traditional stream processing evolved from approaches like SEP, complex event processing, which focused on identifying patterns of events, e.g., detect 3 login failures from the same IP within 1 minute. Modern stream processing frameworks offer more generalized capabilities, record-at-a-time processing. Some simple stream processors can process each event as it arrives, one by one. This is good for simple transformations or filtering. Microbatching. To improve efficiency and leverage existing batch processing concepts, some frameworks, like Spark Streaming, divide the continuous stream into small, time-based batches, e.g., 1-second batches. These microbatches are then processed as tiny batch jobs. Pro can leverage similar fault tolerance and processing models as traditional batch frameworks. Con introduces inherent latency, at least the size of the microbatch interval plus processing time, and can complicate event time ordering issues. Continuous streaming, true stream processing. Frameworks like Apache Flink or Apache Kafka Streams are designed to process events individually and continuously. They don't typically break the stream into artificial time windows unless explicitly requested. Pro, minimal latency, suited for truly real-time applications. Better handling of event time processing and out-of-order events. Con, can be more complex to manage state and ensure exactly once semantics across failures. Key operations in stream processing. Stream processing systems perform various operations on these continuous flows of data. Filtering. Selecting only events that meet certain criteria, e.g., only transactions over $1,000. Transformation. Changing the structure or content of an event, e.g., parsing a log line, converting currency. Joins. Combining events from different streams or joining a stream with a static dataset, e.g., joining a stream of customer purchases with a database of customer profiles to enrich the purchase event. Aggregations. Calculating metrics over a period of time, often within a window. Windowing, because streams are endless, aggregations must be performed over finite windows of time. Different types of windows exist. Tumbling windows. Non-overlapping, fixed-size windows, e.g., some sales every 5 minutes. Sliding windows, overlapping, fixed-size windows, e.g., calculate the average temperature of the last 10 minutes, updated every minute. Session windows. Windows defined by user activity, where a gap in activity closes the window, e.g., a user's uninterrupted browsing session. Stateful processing. Many stream operations require keeping track of past data or aggregating information over time. This requires the stream processor to manage internal state, e.g., current count for a window, last known temperature. This state needs to be fault-tolerant and highly available. 11.4 Messaging queues and stream processing frameworks. The foundation of most modern stream processing architectures is a robust messaging queue or distributed log. These systems act as the central nervous system, capturing events from various producers and allowing multiple consumers to read them reliably. Apache Kafka, the de facto standard for building high-throughput, fault-tolerant, distributed streaming platforms. Kafka is essentially a distributed commit log. Producers write events to topics, logical categories, and these events are appended to a log. Consumers read events from topics, keeping track of their position, offset in the log. Kafka persists events to disk, replicates them for durability and availability, and allows multiple consumer groups to read the same stream independently. It acts as a durable, highly available buffer between event producers and consumers. Analogy: imagine a universal news ticker that records every single event, news story, in the world in the exact order it happens. Producers write to the ticker, and consumers subscribe, reading everything from a specific point onwards, and they can rewind or pause. Other messaging systems. While Kafka dominates the stream processing landscape, other messaging systems like RabbitMQ, Apache ActiveMQ, or Amazon SQS SNS are used for various messaging patterns. Though often not perfectly suited as the primary backbone for large-scale stream processing in the same way Kafka is due to their architectural differences. E.g., transient message storage, focus on queues versus logs. Popular stream processing frameworks built on top of messaging queues. Apache Flink, considered a leading choice for complex, stateful streaming applications due to its strong consistency guarantees, sophisticated windowing capabilities, and efficient state management. It aims for true continuous processing with millisecond latency. Apache Kafka Streams, a lightweight client library for Kafka. It allows developers to build stream processing applications directly on top of Kafka topics using standard Java or Scala APIs. It's often favored for simpler applications or microservices that need to react to Kafka events without deploying a full-fledged streaming cluster. Spark Structured Streaming. Built on the Spark engine, it offers a high-level API which treats streams as continually appending tables, allowing users to write stream processing jobs using Spark SQL or DataFrame's API. It uses micro-batching internally, but presents an abstraction of continuous processing to the user. Good for integrating with existing Spark batch workloads. 11.5 Event-Driven Architectures. Stream processing is a key enabler of event-driven architectures, EDA. In an EDA, components, microservices, communicate primarily by emitting and reacting to events, rather than making direct synchronous requests. Example, in an e-commerce system, a order-placed event is published to a stream. The inventory service consumes this event to decrement stock. The payment service consumes this event to process the payment. The shipping service consumes this event to arrange delivery. This loose coupling and asynchronous communication make systems more resilient, scalable, and adaptable. It allows services to operate independently and evolve without tightly coupled dependencies. It is also a fundamental building block for the saga pattern we discussed in Chapter 8 for distributed transactions. Benefits of event-driven architectures. Decoupling. Services don't need to know about each other directly. Scalability. Each service can scale independently based on its workload. Resilience. If one service fails, others can continue to operate and process events. Auditability. The stream of events provides a durable, ordered log of everything that happened in the system. Challenges of event-driven architectures. Complexity. Debugging distributed systems' asynchronous event flows can be harder. Eventual consistency. Data across different services will be eventually consistent, not immediately consistent. Data duplication. Services might need to maintain caches of data from other services, leading to data duplication. Stream processing is not just a technology. It's a fundamental shift in how we think about and design data-intensive applications. It allows systems to move from reactive to proactive, transforming raw data into immediate, actionable insights and enabling highly responsive, event-driven architectures. While batch processing provides the historical context and deep analysis, stream processing gives us the pulse of the present, making both indispensable in a comprehensive data ecosystem. Next, we will explore how these two powerful paradigms, batch and stream, are often combined to create hybrid architectures. Chapter 12. The future is hybrid. Combining batch and stream processing. We've dedicated separate chapters to batch processing, which thrives on historical data at rest, and stream processing, which deals with data in constant motion. Both paradigms offer powerful capabilities, but in isolation, neither typically provides a complete solution for the demands of modern data-intensive applications. Many real-world scenarios require both immediate insights and comprehensive historical analysis. This necessity has driven the evolution of hybrid architectures that combine batch and stream processing, seeking to leverage the strengths of each while mitigating their weaknesses. 12.1 The Lambda Architecture, Uniting Speed and Accuracy. One of the first widely recognized architectures to explicitly combine batch and stream processing was the Lambda architecture, proposed by Nathan Mars in the early 2010s. It was designed to address the need for both low-latency, real-time query results and highly accurate, comprehensive batch-processed results. The Lambda architecture consists of three distinct layers: batch layer, purpose, stores the master dataset in its raw, immutable form, a master log, or source of truth. It processes all historical data to produce highly accurate, globally consistent views. Processing leverages batch processing frameworks like Hadoop MapReduce or Apache Spark. Output generates precomputed batch views that are then loaded into the serving layer. Analogy. This is like keeping a meticulously accurate, perfectly indexed historical archive of every single event that ever happened. You might update this archive once a day or once a week. Speed layer, real-time layer, purpose. Processes new, incoming data streams in real time to provide immediate, low-latency insights. Processing uses stream processing frameworks like Apache Storm, Flink, or Spark Streaming. Output generates incremental, approximate real-time views. These views contain data that hasn't yet been processed by the batch layer. Analogy. This is a live news ticker that gives you the latest headlines as they break. It's fast, but it might not have the full context or the complete, verified details you'd find in a deeply researched newspaper article, the batch layer. Serving layer, purpose, serves queries by combining the precomputed batch views and the real-time views. Components can use various databases optimized for fast reads, e.g., a relational database, a key-value store, or a specialized serving database. Reconciliation. Queries need to intelligently merge data from both the batch-generated views and the real-time views to show a complete, up-to-date picture. Analogy. When you ask a question, the serving layer quickly pulls the comprehensive information from the historical archive and merges it with the very latest information from the live news ticker to give you the most current and accurate answer available. Pros of the Lambda architecture. Robustness. The raw data in the batch layer is immutable, providing a fail-safe. If anything goes wrong in the speed layer, it can be rebuilt from the batch layer. Accuracy. The batch layer computes definitive results, ensuring ultimate consistency for historical queries. Low latency. For new data, the speed layer provides immediate responses for recent events. Cons of the Lambda architecture. Complexity. Managing two separate processing layers, batch and stream, often means writing and maintaining two distinct codebases for the same logic. This doubles development and operational overhead. Data reconciliation. Combining results from the batch and speed layers in the serving layer requires careful logic to ensure correctness and avoid duplicates or inconsistencies. This can be tricky. Resource overhead. Running two parallel processing systems requires more infrastructure and resources. 12.2 The Kappa architecture. Stream everything. Recognizing the operational complexity of Lambda, the Kappa architecture emerged as an alternative, championed by LinkedIn's Jay Kreps, one of the creators of Apache Kafka. Its core philosophy is a radical simplification: treat everything as a stream. In the Kappa architecture, there is effectively only one processing layer, the stream processing layer. Master dataset. The canonical source of truth is an immutable, ordered stream of events, often stored in a distributed log like Apache Kafka. This log can be replayed from any point in time. Batch processing as stream replay. Instead of a separate batch layer, historical data processing is achieved by replaying parts of the immutable event stream through the stream processor. If your processing logic changes, you simply reprocess the entire historical stream or a relevant portion using the new logic. The output of this recomputation then updates the serving layer. Processing uses a single, powerful stream processing framework like Apache Flink or Apache Kafka streams. Serving layer. Same as Lambda, serving data derived from the stream processing layer. Analogy. Imagine having just one, constantly updated live news ticker. If you want to know what happened a month ago, you simply rewind the ticker to that point and read everything forward from there, processing it with today's understanding. If your way of understanding news changes, you simply reread the entire historical ticker with your new interpretation. Pros of the Kappa architecture. Reduced complexity. A single code base for processing logic, the stream processor, significantly simplifies development and operations. Easier maintenance, fewer systems to manage and monitor. Consistency. Avoids the reconciliation problems of Lambda, as there's only one source of truth and one processing path. Cons of the Kappa architecture. Replaying large histories. For very large datasets, replaying the entire history through a stream processor can still be time-consuming and resource-intensive, potentially impacting development iteration speed. Not all problems fit. While powerful, some batch-oriented analytical problems, e.g., highly complex graph analytics needing multiple passes, might not map naturally or efficiently to a purely streaming model. State management. Managing large, consistent state in a stream processor during long replays requires robust capabilities from the chosen framework. 12.3 Unifying batch and stream processing. The Holy Grail. The inherent complexities of both Lambda and Kappa architectures spurred advancements in stream processing frameworks themselves. Modern systems like Spark Structured Streaming and Flink have made significant strides in truly unifying the batch and stream processing paradigms within a single API and runtime. The core idea is that batch is simply a bounded stream, and a stream is an unbounded table. You write your data processing logic once using a unified API. The framework then adapts its execution strategy based on whether it's processing a finite historical dataset, batch, or a continuous stream of new events. For example, Spark Structured Streaming treats incoming data as an unbounded table that constantly has new rows appended. You write standard Spark SQL or data frame queries, and Spark continuously applies them to the new data, essentially transforming your batch logic into streaming operations. This unification represents a significant step towards simplifying hybrid architectures, reducing cognitive load for developers, and improving operational efficiency. It enables truly flexible data pipelines where the same code can provide both real-time alerts and historical aggregates. 12.4 Beyond processing, data lakes and data meshes. As organizations accumulate ever-increasing volumes of diverse data, simply having processing engines isn't enough. The way data is stored, organized, and shared is equally crucial. This brings us to the concepts of data lakes and the emerging data mesh. 12.4.1 Data lakes, centralized raw data repository. A data lake is a centralized repository that allows you to store all your structured, semi-structured, and unstructured data at any scale. Unlike a traditional data warehouse that often requires a predefined schema before data can be loaded, schema on write, a data lake stores data in its raw, original format. The schema is applied when the data is read, schema on read. Role in hybrid processing. Data lakes often serve as the raw, immutable source for both batch and stream processing layers. The stream processor might subscribe to real-time events that are also simultaneously written to the data lake for long-term storage. Batch jobs then transform and aggregate data from the data lake for analytical purposes. Pros, flexibility, stores all data types, enabling future analysis that wasn't conceived when the data was collected. Cost-effective storage generally uses cheap commodity storage, e.g. S3, HDFS. Source for AI ML, raw, untransformed data is invaluable for machine learning models. Cons, data swamp risk. Without proper governance, metadata, and tools for discovery, a data lake can become a chaotic, unusable repository where finding useful data is like searching for a needle in a haystack. Security and governance. Ensuring data quality, access control, and compliance across a vast, heterogeneous dataset is challenging. 12.4.2 Data mesh. Decentralized data ownership. While data lakes centralize storage, they often perpetuate a centralized data team bottleneck. The data mesh is an emerging decentralized architectural paradigm that shifts the ownership and operation of analytical data from a centralized data team to domain-oriented teams. Core principles, domain ownership. Instead of a central data team owning all analytical data, individual business domains, e.g., marketing, sales, product, are responsible for their own data. Data as a product. Each domain treats its analytical data as a product, making it discoverable, addressable, trustworthy, self-describing, and secure. Data is served via APIs or well-defined interfaces. Self-serve data platform. A centralized platform team provides self-serve capabilities, tools, infrastructure, governance that enable domain teams to build and operate their own data products. Federated computational governance. Data governance operates at a global, federated level, setting standards and policies, but execution occurs collaboratively across domains. Relates to hybrid processing. In a data mesh, each data product, owned by a domain, might embody its own batch and/or stream processing pipelines, chosen and operated by the domain team itself. This is a move away from monolithic, centralized data pipelines towards a distributed ecosystem of data services. Pros, scalability for large organizations. Scales organizational adoption of data by decentralizing responsibility. Agility, domain teams can react faster to their specific data needs. Increased domain expertise. Data products are built and maintained by those who best understand the data. Cons, significant organizational change requires a fundamental shift in mindset and team structure. Interoperability challenges. Ensuring discoverability and consistent interfaces across many independently managed data products. Initial investment. Building the self-serve platform and establishing federated governance can be a large undertaking. 12.5 Data lineage and governance. Maintaining order in chaos. As data architectures become more hybrid and decentralized, tracking and managing the flow of data becomes incredibly important. Data lineage refers to the life cycle of data, tracking its origin, transformations, and destinations. It's the ability to trace data from its source system through all processing steps, batch and stream, to its final consumption point. Why it's crucial: troubleshooting, essential for debugging when unexpected data appears or disappears. Compliance and audit. For regulations like GDPR or HIPAA, knowing where personal data came from and how it was processed is mandatory. Impact analysis, understanding what happens if a source system changes its data format. Trust, building confidence in the data's quality and accuracy. Data governance encompasses the policies, processes, and tools used to manage and ensure the quality, security, and usability of data across an organization. In hybrid and mesh architectures, good governance is paramount to prevent data swamps in lakes or unmanageable complexity in meshes. It ties back directly to the maintainability pillar we discussed in Chapter 2. Conclusion: the era of choosing rigidly between batch and stream processing is largely over. Modern data-intensive applications require both, often woven together in sophisticated hybrid architectures like Lambda or, increasingly, unified platforms. Furthermore, the sheer volume and diversity of data demand equally sophisticated strategies for data storage and management, leading to the rise of data lakes and the more recent paradigm of data meshes. All these advancements underscore a critical need for robust data lineage and strong data governance to tame the inherent complexity. These architectural patterns and choices define the cutting edge of data system design, empowering organizations to derive comprehensive and timely insights from their ever-growing data ecosystems. Chapter 13, Architectural Patterns and Case Studies. We've journeyed through the foundational concepts of data-intensive applications. From the crucial pillars of reliability, scalability, and maintainability, to the intricacies of data models, storage mechanisms, replication, partitioning, and the complex world of distributed transactions and consensus. We've explored the distinct, yet often merging worlds of batch and stream processing. Now, it's time to see how these individual components fit together to form complete, functioning systems. This chapter will bridge the gap between theoretical concepts and practical implementation. We'll examine common architectural patterns that leverage these principles, and then briefly explore how major companies have applied these ideas, and sometimes invented new ones, to solve their immense data challenges. The goal isn't to provide a blueprint for your next billion-dollar startup. No two systems are identical, but rather to illustrate how the principles we've discussed are applied in the wild, and how different choices lead to different outcomes. 13.1 Common Architectural Patterns. Architectural patterns are reusable solutions to common problems that arise in software design. They provide a high-level blueprint, guiding decisions about how components should interact and where specific concerns should be addressed. 13.1.1 CQRS. Command Query Responsibility Segregation. Traditionally, most applications use a single data model and database for both reading and writing data. However, the demands of reading, queries, and writing commands are often very different. Queries typically need fast retrieval, often involve complex filters and joins, and serve user interfaces directly. Commands, e.g., creating, updating, deleting data, emphasize data integrity, transactional consistency, and usually have simpler access patterns, e.g., write a single record. CQRS addresses this by suggesting that we separate the model used for updating data from the model used for reading data. Command side handles all write operations. It processes commands, e.g., change customer address, validates them against business rules, and updates the write model database. This database is optimized for writes and transactions and can often be a traditional relational database or sometimes an event store, as we'll see with event sourcing. Query side uses a separate read model database specifically optimized for queries. This read model is built by passively listening to changes events from the command side. It can be highly denormalized, perhaps a specialized search index, a document database, or even just a flat key value store tailored to specific UI representations or reporting needs. Example: imagine an e-commerce site. When a customer places an order, a command, the order service might write that to a transactional database. This service then emits an order placed event. A separate order reporting service consumes this event and updates a denormalized view in a fast, read-optimized database. When a customer wants to view their order history, the UI queries this read-optimized database directly. Benefits: scalability. Read and write workloads can be scaled independently, Often using different technologies, replication helps scale reads. Optimized models. Each model, write and read, can be optimized for its specific purpose, improving performance for both. Flexibility. The read models can be easily rebuilt or adapted without impacting the write model. Security. Commands might require different access controls than queries. Trade-offs. Complexity. Significant increase in architectural complexity. You now have two distinct data models, two databases, and a mechanism to synchronize them, often an event bus. Eventual consistency. The read model will likely be eventually consistent with the write model. Users might experience a slight delay before their changes are reflected in the query side. 13.1.2 Event sourcing. Closely related to CQRS. Event sourcing is a pattern where all changes to application state are stored as a sequence of immutable events. Instead of storing the current state of an entity directly, e.g., a customer record showing their current address, you store the history of how that state was reached, e.g., customer created, address changed to X, email updated to Y. The current state is then derived by replaying all these events in order. How it works. When an operation occurs, a command, it doesn't directly update a database table. Instead, it generates an event, e.g., order placed event, product quantity decreased event. These events are saved to an append-only event store, a distributed, durable log like Kafka or a specialized event store. The current state of the application, e.g., the inventory level, is built by reading and applying all relevant events from the beginning of time. Read models, projections, are built by consuming the stream of events and transforming them into optimized views, often in separate databases, complementing CQRS. Example, for an inventory system, instead of updating a product table's stock level column, you would record events like product added event, product shipped event, product damaged event. To find the current stock, you sum up all product added event quantities and subtract all product shipped event and product damaged event quantities. Benefits: full audit trail. A complete, immutable history of all state changes, invaluable for auditing and compliance. Enhanced debugging can easily reconstruct the state of the system at any prior point in time. Temporal queries can ask questions like, what was the stock level last Tuesday at 3 p.m.? Basis for event-driven architectures, natural fit for publishing events that other services can subscribe to. Resilience. High availability if the event store is resilient. Red models can be rebuilt if lost. Trade-offs. Complexity requires a fundamental shift in thinking about data and state. Querying challenges. Direct querying of the event stream is difficult, typically requires building and maintaining separate read models, further leveraging CQRS. Schema evolution of events. Modifying event schemas can be complex, as old events must still be replayable. 13.2 Real-world examples and lessons learned. Let's briefly examine how some of the world's most data-intensive companies tackle their challenges, applying the principles we've discussed. 13.2.1 Social media feeds, e.g., Twitter, Facebook. Challenge: millions, even billions of users. Billions of posts, likes, shares. Feeds need to be personalized and delivered in near real time. High read and write volume. Approach often seen: polyglot persistence. No single database can handle everything. Key value stores for user data, session information, short messages. Graph databases for social connections, who follows whom, who is friends with whom. Search engines, e.g., Elasticsearch, for searchable content. Replication and partitioning, massive horizontal scaling is critical. Data is sharded extensively, e.g., by user ID. Feed generation, two primary models. Fan out on write. When a user posts, the content is immediately pushed to the inboxes, message queues, or personalized feed stores of all their followers. This is common for high fan-out, many followers scenarios, ensuring low read latency. Facebook often uses variations of this. Fan-out on read. When a user opens their feed, the system pulls content from all the people they follow, aggregates it, and then presents it. This is more common for systems with fewer followers per user. Twitter often uses a hybrid approach, with a fan-out on write for active users and fan-out on read for non-active users. Caching. Extensive multi-layer caching. proxies, CDNS in memory caches is crucial to reduce database load. Stream processing, used for real-time analytics, spam detection, trend analysis, and feed ranking, e.g., personalizing what you see in your feed. Consistency, feeds are typically eventually consistent. A new post might appear simultaneously for some followers, but take a few seconds longer for others. This is an acceptable trade-off for speed and availability. Lesson: extreme scale forces radical solutions. Simplicity in core data access patterns, e.g., key-value lookups, and embracing eventual consistency are key strategies. 13.2.2 E-commerce, e.g., Amazon. Challenge: product catalogs, orders, payments, shipping, recommendations, customer reviews. High transaction volume, strict consistency for financial operations, personalized experiences. Approach often seen: polyglot persistence as a philosophy. Amazon historically pioneered the idea of using the right database for the right job, leading to DynamoDB, their key-value store product, and Relational Database Service, RDS, offerings. Relational databases, for critical transactional data like orders, invoices, and payment processing, where ACID is non-negotiable. Document databases, for flexible schemed data like product catalogs, product attributes vary widely. Key-value stores, for user sessions, shopping carts, caching. Graph databases, for recommendation engines, customers who bought this also bought that, fraud detection. Search engines, for product search. Event-driven architecture, order fulfillment, inventory updates, shipping notifications, and payment status changes are often propagated as events through messaging systems, like Kafka or SQS, enabling loose coupling and resilience across many microservices. Batch processing, for reporting, complex analytics, machine learning model training, e.g., recommendation algorithms run on historical purchase data, and inventory forecasting. Stream processing, for real-time recommendations, clickstream analysis, fraud detection, and dynamic pricing adjustments. Lesson: embrace diversity in data stores. Different data has different consistency, performance, and modeling requirements. Microservices and event-driven architectures are key to managing the complexity. 13.2.3 Netflix, streaming service. Challenge: delivering massive amounts of video globally, handling millions of concurrent users, providing personalized recommendations and robust billing. Approach often seen: content delivery networks, CDNS. The actual video files are distributed globally to CDN edge nodes, reducing latency for actual streaming. Cassandra column family database. Heavily used for almost all non-video data, including user watch history, user preferences, configurations, and internal operational data. Cassandra's write performance and multi-data center replication capabilities make it ideal for this scale, even with eventual consistency. Kafka serves as the central nervous system for data, collecting every user interaction, play, pause, fast forward, operational log, and billing event into various high-throughput streams. Apache Flink/Spark, used extensively for stream processing. Flink is particularly important for stateful stream processing related to recommendations, real-time analytics, and anomaly detection in the user experience. Microservices architecture. Netflix is famous for its pioneering adoption of microservices, with hundreds of independent services communicating over lightweight protocols and event streams. This enables independent teams, rapid development, and high availability. Cloud native leverages cloud provider infrastructure (OS) extensively, relying on its elasticity and managed services. Lesson: focus on separating concerns, leveraging specialized databases for their strengths, and building highly asynchronous, resilient workflows. Operational excellence in a distributed environment is paramount. 13.3 Choosing the right tools for the job. These case studies underscore a critical meta lesson. There is no single best database, framework, or architectural pattern. The optimal solution is always context-dependent. When designing your own data-intensive application, consider your core requirements, prioritize the big three. What are your non-negotiables for reliability, scalability, and maintainability? Do you need strict consistency for financial transactions, or can you tolerate eventual consistency for a social feed? How many users will you have? How fast is your data growing? Data characteristics. What kind of data are you storing? Is it highly structured, graph-like, or flexible JSON? What are your most frequent access patterns? Key lookups, range queries, aggregations, relationship traversals. Team expertise. Your team's familiarity with a technology is a huge factor in its maintainability. A technically superior solution is useless if your team can't implement, debug, and operate it effectively. Ecosystem and community. A vibrant open-source community, good documentation, and strong commercial support can make a difference in the long run. Cost. Hardware, software licenses, operational overhead, and developer time all factor into the total cost of ownership. Start simple and iterate. Don't over-engineer from day one. Many successful systems start with a single, well-understood relational database and scale incrementally only when performance bottlenecks or new requirements necessitate more complex solutions like replication, partitioning, or polyglot persistence. The future is hybrid, isn't a mandate to use every tool, but an acknowledgement of what might be needed eventually. Designing data-intensive applications is an ongoing challenge, a blend of science and art. It requires not just technical prowess, but also a deep understanding of business context, user needs, and the inherent trade-offs in distributed systems. As the landscape continues to evolve, our ability to learn and adapt will be more valuable than ever. In our final chapter, we'll cast our gaze towards the horizon, exploring emerging trends and the continuous journey of innovation in data systems. Chapter 14, Beyond the Horizon. Emerging Trends in Data Systems. We've covered a vast landscape, from the fundamental pillars of system design to the intricate dance of data models, storage engines, distributed transactions, and the powerful paradigms of batch and stream processing. We've seen how these concepts are woven together in complex architectures that power today's most demanding applications. But the world of data is not static. It's an arena of relentless innovation and evolution. As we conclude, it's important to cast our gaze forward. While the core principles of reliability, scalability, and maintainability remain timeless, the technologies and patterns used to achieve them are constantly shifting. New challenges arise, from the ever-increasing volume and velocity of data, to the growing complexities of governance and the ethical considerations of artificial intelligence. This chapter will explore some of the exciting emerging trends and ongoing shifts that are shaping the future of data-intensive applications. 14.1 Serverless Data and Managed Services. One of the most significant trends is the increasing abstraction of infrastructure management through serverless and fully managed database services. Cloud providers AWS, Azure, Google Cloud are leading this charge. Serverless databases. Databases like Amazon Aurora Serverless, Google Cloud Firestore, or Azure Cosmos DB, with serverless capacity mode, allow developers to focus purely on application logic without provisioning, scaling, or managing database servers. The database automatically scales capacity up and down based on demand, and you typically only pay for the actual reads, writes, and storage consumed. Impact drastically reduces operational overhead and the need for specialized database administrators, DBAs, for routine tasks. It accelerates development by removing infrastructure concerns. Trade-offs can introduce vendor lock-in, and the serverless cost model can sometimes be unpredictable for very spiky workloads if not carefully managed. Less control over the underlying infrastructure and tuning. Managed services. Beyond serverless, most major cloud providers offer fully managed versions of popular open-source databases, e.g., Amazon RDS for PostgreSQL/MySQL, Azure Cosmos DB for MongoDB API, Google Cloud Bigtable for HBase API. Impact provides significant operational relief, handles backups, patches, scaling, and high availability. Focus shift. Developers and architects can spend less time on undifferentiated heavy lifting and more time on core business logic and data modeling. This trend effectively pushes the responsibility for reliability, scalability, and maintainability of the underlying data infrastructure from individual teams to highly specialized cloud providers, enabling organizations to move faster. 14.2 Data virtualization and data fabrics. As companies adopt polyglot persistence and build increasingly distributed data ecosystems, including data meshes, the problem of data sprawl becomes acute. How do users or applications query data when it's scattered across dozens of different databases, data lakes, and services, each with its own API and data model? Data virtualization is a technology that creates a single, logical view of data from multiple disparate sources, without physically moving or duplicating the data. It acts as an abstraction layer, allowing users to query data using a unified interface, e.g., SQL, as if it were all in one place, while the virtualization layer dynamically fetches and integrates data from the underlying sources. Impact simplifies data access for reporting, analytics, and application integration, reduces data duplication and ETL complexity. Challenges: performance can be an issue if the underlying data sources are slow or if complex joins across highly distributed systems are required. The concept of a data fabric builds on data virtualization, but extends it to provide a more holistic, enterprise-wide approach to data management. A data fabric aims to provide a unified, intelligent, and automated platform for data integration, governance, and access across hybrid and multi-cloud environments. It's often infused with AI and machine learning to automate data discovery, quality, and transformation. Vision: a future where data is seamlessly discoverable, understandable, accessible, and governed, regardless of where it resides or what its format is. 14.3 Data observability. Just as software development shifted towards observability for applications, monitoring everything from logs to traces to metrics, data systems are now embracing data observability. This discipline focuses on gaining a deep understanding of the health and reliability of data across the entire data lifecycle. Key pillars: freshness: is the data up to date? E.g., has the nightly batch job completed successfully? Completeness: is all expected data present? E.g., are there gaps in the event stream? Validity quality: is the data accurate and reliable? E.g., are values within expected ranges? Is the schema consistent? Volume: is the amount of data what's expected? E.g., sudden spikes or drops in records processed? Latency: how long does it take for data to move from source to consumption? Lineage: where did the data come from and how was it transformed? As discussed in Chapter 12. Impact: proactive detection of data quality issues or pipeline failures before they impact business decisions or downstream applications. Builds trust in data. Tools: a new ecosystem of tools is emerging for data observability, often leveraging machine learning to automatically detect anomalies in data patterns. 14.4 Machine learning integration in data pipelines. Machine learning is no longer a separate, siloed activity. It's increasingly becoming an integral part of data-intensive applications and pipelines, MLOps, the discipline of operationalizing machine learning models. It involves building automated pipelines for data preparation, model training, model deployment, and continuous monitoring of model performance in production. This relies heavily on stream and batch processing capabilities, often leveraging tools like MLflow, Kubeflow, and various cloud ML platforms. Real-time inference: deploying machine learning models to make predictions or decisions in real time within stream processing pipelines, e.g., fraud detection, personalized recommendations delivered instantly. Automated data quality: using ML to detect anomalies or predict data quality issues within data streams, contributing to data observability. Feature stores: shared, centralized repositories for storing and serving engineered features, data attributes derived for ML models, consistently for both training and real-time inference. 14.5 The growing role of data governance and ethics. As data becomes more pervasive and powerful, so do the responsibilities associated with it. Stricter regulations. Laws like GDPR, Europe, CCPA, California, and others worldwide impose stringent requirements on how personal data is collected, stored, processed, and deleted. This mandates robust data governance, lineage, and access controls. Data ethics and bias. The increasing use of AI and machine learning raises critical ethical questions. Is the data used to train models unbiased? Are the algorithms fair? How do we ensure transparency and explainability in automated decision-making systems? Privacy-enhancing technologies, PETs, technologies like homomorphic encryption, federated learning, and differential privacy allow computations or model training to be performed on encrypted or anonymized data, reducing privacy risks. These are not just technical challenges. They require deep collaboration between engineers, legal, compliance, and product teams to ensure data is used responsibly and ethically. 14.6. The enduring value of first principles. Despite these rapid advancements, it's crucial to remember that the fundamental principles we discussed at the beginning of this book remain timeless. The specific technologies may evolve, but the core challenges of reliability, scalability, and maintainability will always be present. Reliability. Hardware and software will always fail. Networks will always be unreliable. Designers must continuously build systems that gracefully handle these realities. Scalability. Data volumes and user demands will continue to grow. Scaling strategies, whether manual or automated by serverless platforms, will always be needed. Maintainability. Systems will always need to be understood, operated, and adapted by humans. Complexity is the enemy of maintainability, and architects must constantly fight against it, even as distributed systems inherently introduce it. These guiding principles provide a stable compass in a constantly shifting technological landscape. The ability to abstract away infrastructure details through managed services and serverless offerings is fantastic, but it doesn't remove the need to understand what is happening under the hood when things go wrong, or why certain architectural patterns are chosen over others. Conclusion: continuous learning and adaptation. Designing data-intensive applications is a fascinating and profoundly challenging field. It requires a blend of computer science fundamentals, practical engineering sense, and a strategic understanding of business needs. The journey of learning in this domain is endless. New technologies emerge, old ones gain new relevance, and the boundaries between concepts like batch and stream blur further. The most valuable skill in this ever-evolving data ecosystem is not mastery of a specific tool, but rather the capacity for continuous learning, critical thinking, and the ability to apply fundamental principles to novel problems. Embrace the complexity, understand the trade-offs, and relentlessly strive to build systems that are not just clever, but truly reliable, scalable, and maintainable. The data jungle is vast and ever-expanding, but armed with these insights, you are now much better equipped to explore and build within it. Further reading and resources. Kleppman Martin, Designing Data-Intensive Applications. The Big Ideas Behind Reliable, Scalable, and Maintainable Systems. O'Reilly Media, 2017. Highly recommended as the definitive modern overview. Tannenbaum, Andrew S., and Martin Van Steen, Distributed Systems, Principles and Paradigms. Pearson, Fowler Martin, Patterns of Enterprise Application Architecture. Addison Wesley, IEE Transactions on Knowledge and Data Engineering, TKDE, VLDB, SIGMOD, OSDI, SOSB Conferences for Academic Rigor. Engineering blogs from technology companies, Google, Facebook, Netflix, Amazon, LinkedIn, Uber, etc. These provide invaluable real-world case studies and operational insights. Open-source project documentation for Apache Kafka, Apache Spark, Flink, Cassandra, Kubernetes, etc. By staying curious, continuously experimenting, and engaging with the vibrant community of data engineers and architects, you will be well prepared for the beyond the horizon, challenges and opportunities in this exciting field.